So, good morning, good afternoon, good evening to all of you. Thank you for joining us for day 2 of the Sustainable Energy Futures 2021 Annual Conference. I have the pleasure with my colleague Anna for hosting you today, and I hope you found, those of you who attended yesterday, found the 3 sessions very interesting and the Q&A sessions even more interesting. And I was certainly blown away by Damalola's keynote speech yesterday, which was very, very thought-provoking. So without further ado, I would like to just hand over to Professors Cora and Green, who will then take us into the first day of the first session. Thank you.
Thank you for that. Could I please add my welcome to everybody? Welcome to all of the students who will be presenting this afternoon or who presented yesterday, to the supervisors of these research projects in the college and in industry, to any friends, families and supporters who've come along as well. You're all very welcome to what I'm sure will be a fascinating series of talks and indeed a keynote address before that. This is a culmination of a year's effort by our students. We throw a lot of quite difficult material across a broad range of topics at the students, and they always respond to that magnificently. And then in this sort of second phase of the course, where students do their individual research projects, there's an astonishing range of topics covered, and it's amazing to see what our students are capable of achieving when let loose on these testing and difficult questions. I think I also want to thank our students as well for showing the forbearance and the fortitude they've had to in order to get through what has been a difficult year with the pandemic. Nonetheless, it remains my favourite class to teach. I was teaching back in November and December. It's a little while ago now, but this is a great class to teach because of the enthusiasms and the engagements and the knowledge and the curiosity of this particular cohort of students from all their various backgrounds. Good luck with the presentations this afternoon. I'm sure they'll be magnificent, and good luck with your future careers that you move on to now that you have completed all of the key tasks here at Imperial College. I'll hand over to my colleague, Professor Corey.
Thank you, Tim, and a warm welcome from me for this session. I'm sure that it's going to be a very enjoyable celebration of your wonderful research projects. And I just wanted to add to what Tim just said, that you're a gift to your supervisors, and your supervisors know this. This is why they spend quite a lot of time with you, and they enjoy supervising your thesis projects. So today is the day where the fruits of your hard work are visible to your classmates, your friends, ourselves, and the wider community, and it's a day when you should be extremely proud of yourselves. And the last thing that I am going to say, maybe some of you have not heard yet that Professor Tim Green will step down from his role as co-director of the Energy Futures Lab at the end of this year in December. He has led our institute single-handedly for 5 years to an extremely successful position, also looking after the MSc course and yourselves and the alumni that came before you, and the wider community of students for a very long time. I have had the pleasure to work with him and be impressed by his academic ability and his commitment to his role at EFL and also the college. And I wish him all the best in the future. I hope that you will join me in doing so. And I know that he's going to be our friend and colleague still at the college, and we will still have the pleasure of him teaching in the MSc course and interacting with him for the years to come. And if Tim allows me.
Well, I've got to thank you for your warm words already, Anna. That's very kind of you to have said all of that. I wonder what you're going to say next.
I am going to say that I hope that you have many healthy and happy years, and the joy that you have given is actually given back to you in many different ways, which I do not want to say what it might be. So okay. Back back to the proceedings, and can I please ask, is it Avik who is going to take us forward next?
Yes, absolutely.
Thank you, Avik.
Thank you, Professor. So I have the pleasure in introducing our keynote speaker for today, which is we have Stephen Lorimer from the Centre of Net Zero. Now, Stephen is going to speak to us about mapping energy transitions and understanding how policy, buildings, industry and wealth intersect and interplay. So Stephen is the one of the founding team members of the Centre for Net Zero, which is powered from Octopus Energy, spun out from Octopus Energy, and he is responsible for their partnerships and building a community of researchers around our buildings, how our work building faster and fairer paths to net zero. He came to the Centre from the Civil Service, where he managed teams covering government data sharing policy and science policy for the NHS COVID-19 app. At the Greater London Authority, he developed the commercial model for the London Office of Technology and Innovation, and he's also led the research that delivered the Smarter London Together roadmap, which is the city's approach to digital transformation of the city services. Stephen has a PhD in energy and built environment from the Bartlett School of the Built Environment at UCL, where he modelled domestic energy demand. And before his work in energy and technology, he worked as an urban design consultant to local authorities across the UK, Ireland, and France. Stephen does have a link to Imperial, so as a part of his postdoc work, he actually worked as a program manager for the Sustainable Society Network, supporting UK research in water, waste, energy, local and national transport infrastructures. And with that, he's got a lot of experience behind him, and I'm going to hand over to Stephen to give us what I expect to be a very, very interesting talk. Thank you, Stephen.
Hi everyone. Thanks very much for the introduction. And there we go. Right. I think I'm in the position where everyone can see my screen now. So thanks very much for the introduction, and I'll first go and say thank you for the invitation. It's sad that I can't be in a room at Imperial where I used to spend a couple of years. As I've said, working on this thing, I actually had to go back to the Wayback Machine and actually find my old website that we set up for the network. So this is my time that I spent a couple of years at Imperial as the program manager for the network that I think it's over before. So I just thought I'd kind of say that as a bit of an introduction to myself. That it's a place that I remember very fondly. The time that I spent about 7-8 years ago. But I first want to say we're a new organization, and so a lot of you probably are wondering what is the Centre for Net Zero. It is a open research lab where we're looking to pioneer research that gets us to net zero quickly, fairly, and affordably. And just the idea of the story so far of ourselves, we've been set up as a non-commercial unit of Octopus Energy, which, as many of you probably are aware, that they're one of the unicorns in the UK. They've been set up where their business model really is set up. So if the renewable grid really does happen, they're in the position to take advantage of that more than other companies. But we are kind of an arm's length from them as a separate legal entity, and we have the kind of independence you would want as an open research lab in the future. And we're working to really co-create world-class research with others. We're trying to engage others through our communication, and we're promoting open technology and open data throughout the energy system. And the kind of research that we're looking at and trying to think about what we do and what we don't do. We have real data because we have the database of Octopus Energy and their customers and their consumption and their surveys of who owns low carbon technologies. And we're focused on kind of using that individual level data to model people and really use that to embrace systems and learn by doing. And yes, apologies to those who are in the academic space. Maybe we don't get onto 3-year research projects, and we are on kind of shorter timescales than that. And the kind of feedback loops we're looking at around policy, adoption of technologies, awareness of people that they exist, and really kind of ours, is the supply chain available to do so? And really working very hard at understanding household behavior, using demographics, and what technologies they own, what's inside buildings, and try to get an idea of how people use energy and how likely they are to adopt new technologies, because we've been very slow, especially in the domestic sector, buildings in general, adopting new technologies in the United Kingdom, partly because a lot of you probably studied the setup of the natural gas network is so pervasive and so cheap, especially in heating. And in personal transport, it's set up so much for car ownership, using fossil fuels, and kind of where do you deal with the market failures in charge points and making electric vehicles work. And so we're really focusing on 2 areas right now of heating the domestic sector, and kind of really focus on what are those pathways towards developing photovoltaics, heat pumps, other supplies that will come in. What is the integrity of the grids when that transition happens? And we're also working on personal and business fleet transport. And when it's arrive at scale, how do we actually get them? How do we actually address the bottlenecks in charge points, the grids, matching supply and demand as we go forward? So I did say that I wanted to really focus on like how do you actually communicate with different audiences and actually get them to get a feel for what you're describing as the energy transition and the problems and challenges and the solutions that you want to overcome. And one of them is through maps and visualizations, and is something that I feel very strongly about using, not just because I trained as a town planner originally, and those of us who did that usually love maps, but also kind of because of the experience I've had working with data in government and communicating with ministers and decision makers, and their real demand for visualizations to be able to understand what is going on, like surveillance and the idea that it's not surveillance of crime or surveillance like terrorism, but actually, and that has been a weakness in governments, has been exposed in the COVID pandemic, making decisions without much knowledge at the right level of detail for what is happening. And that's something that's been, and one of the things that those of us learned in the pandemic over the last few years is the value, this is the classic map that came out in the 19th century. I'll give you a couple of them that came in the 19th century. That was founded epidemiology, help us understand the value of individual data based on location in this instance of what is the cause of disease. And so John Snow in this pump right here is actually the pub is called John Snow on the corner. Those of you who've been to Stowe probably have seen it. Where he mapped out who was dying from cholera, and there was no mistaking where the infection was coming from as a result of this. But how do we deal with this with GDPR and other issues in aggregation? Yes, those are definitely things to go through. In aggregation, this is another classic map from the same era by Charles Minard in France, and this is how he visualized Napoleon marching up to Moscow, losing troops as he went along the way and retreating backwards, and winding up, starting at 422,000 and winding up with 10,000 at the end. And so these are 2 of the classic visualizations and maps that kind of founded the discipline over time. So yes, give us the maps. as you're probably thinking. I'll give you a quick series of the kind of maps that we're looking at. Why is population is evenly distributed across the UK? Well, it's clearly not. It clusters in certain regions that you see on the left. It clusters in in flats, and it clusters by different types of tenure that are out there. Now, if you match up where is it poorly insulated, what regions, and try to think of like, well, why, for example, you can see in London, they have many more flats in London, but on the left you see that there are very few that are poorly insulated, and then you can also look through kind of what is the difference between those who can afford to insulate their homes, who are owners, and those decisions are not in their hands, those who are tenants as well. And know that kind of one of the really valuable data sets in the UK that they use is the index of multiple deprivation. They kind of take a number of different socioeconomic factors and rank all the different areas in each nation from 1 to 30,000 or whatever the number of census areas that they use in the UK. And we can clearly see that these areas which are very less deprived in England, in the southeast, are getting many more dwellings built in them per year because of market forces. And when we build new buildings, they're more energy efficient. And so are these places that the market is providing new housing just kind of making us feel like we're delivering energy efficiency from people who can afford it, and versus those who can't afford and have less choice? These are things that are important to know. Another part that we're thinking about is, well, where is the natural gas network? This is kind of physical constraints, not just socioeconomic constraints that are out there. Is there a connection between when you're developing district heating networks and where there's less of a gas grid? So is it simply responding to the less availability of gas, or is it people who are or is it real policies that are promoting these technologies over time? And also we're trying to think a lot about, well, when we have a lot more heat pumps or electric vehicles, does it matter where they're clustered near sources of renewable energy, ones like these, to keep the integrity of these grids over time? Those questions of, should the UK be directing more these technologies or subsidizing these geographically towards the coastlines where they're closer to renewable energy or wind farm projects, or closer to hydrogen projects where they're happening? Those are kind of questions that's really kind of easy to start to tease out when you start mapping. Another part that everyone is concerned about is that installers don't have the skills to install heat pumps in the UK, and you can see the huge difference, and look at the scale between the number of installers that know how to install gas boilers versus those who know how to install air source heat pumps or ground source heat pumps. The numbers are certainly staggering to know that if we actually have supply of heat pumps in the UK, we don't have the installers that are trained to do it. We don't have, and the number of training centers that are set up, they're starting to pick up, but are they in the right place as well? And finally, kind of one of the projects that I've worked over the last month or so is assembling what we call a home decarbonization index, taking all these factors of how many people are have acquired heat pumps, acquired solar panels, have acquired electric vehicles over the past decade, and where are the types of places where this has happened. They've happened in places where they have low population density, high home ownership, high car ownership. In essence, those who have control over their own land and have availability of land, which are low-hanging fruit of individual decisions that are over time. And really, to deliver at scale, it's showing that in places where we need collective decisions, whether it be you live in a block of flats, you're a tenant of a housing association, you're somebody who don't have your own street parking, and you have to have a permit to park on the street from your borough or from your from kind of your freeholder, if you will. Those places, those kind of non-cost barriers are very much very much evident when you start to map out where these technologies have been adopted over time. And it kind of shows us that really kind of it does. You've probably seen this graph loads of times. That the diffusion and innovations, we're still in this kind of innovator early adopter phase with electric vehicles and heat pumps and other low carbon technologies. And so how do we actually move it on from that phase? And we need to move it on, and it's clear from the kind of mapping, kind of just getting an idea of what is happening across the UK, is too often policy is dependent on people having wealth to make the right, in quotation marks, individual decision to acquire sustainable technologies with a small amount of subsidy and nudge out there. Maybe that subsidy is just going to people that would have taken those action anyway at the moment. And how do we actually really resolve market failures to get us further along this innovation curve? So this is a bit of a recap of the conclusions, from just showing you these maps today. We know that poor installation or kind of poor uptake of these technologies really, in the end, is unevenly distributed, and after kind of thinking through kind of who's getting the credit for these technologies, why is innovation not happening in heating and transport? Where is the installer skills going to come into it? All of those, and knowing that those who have the most means and the most flexibility are the ones who are adopting these technologies and are the first movers, which they often had in innovation. Those who have the least to lose are often ones to take the risk first, which is often understandable. So that's a quick tour of. Thank you for getting us, having me to kind of visit, in quotation marks, Imperial again today. Do get in touch if you have projects that you think that you could work in partnership with our centre in the future. We're really focused on domestic heat and transport at the moment. We'll go further afield from the UK to other countries and work with cities and regions of localized models, how they might drive in the future. And if you want to see more, we have 2 posts that I can send the links afterwards. One is called 10 Maps that Explain the challenge of the energy transition in the UK, and the other one is the Home Decarbonisation Index. So that's back to you.
Great. Thank you, Stephen. Thank you for yet another thought-provoking keynote speech. I have a newfound appreciation of maps and data, so thank you very much for that. I should say we're not taking questions now, but Stephen will hopefully be joining us at the dinner, at the conference dinner this evening. And so should anyone in London have any questions who are attending the dinner, I'm sure Stephen won't mind in actually answering those questions for you. So without any further ado, I will move on to session 1, which is energy systems transition for industry and how legacy industries can fit into the energy transition. So we'll take it away with those presentations. Thank you.
So welcome everyone to this presentation where we'll tell you about the energy system transition for the commercial and industrial sectors. Our team is very happy to be here today to introduce you to the challenges for decarbonization, as well as some technologies, strategies, and policies that should be applied for these sectors. Indeed, you know that we are in the middle of crucial times for the future of the planet. During the Paris Agreement, 197 countries committed to limit global warming to 1.5 degrees. Industries and businesses are critical sectors where action should be taken to reach this objective. Indeed, in the UK, they account for roughly 25% of the CO2 emissions. However, the IPCC released a month ago their sixth report to assess the state of the climate, and they strongly highlight that the current trajectory leads us far above the 1.5 degree objective. It means that even though efforts have been made, a lot remains to do. Today, if we have decided to tell you about businesses and industry, it's because they share characteristics, notably a struggle to decarbonize due to the commercial purpose of their activities, but at the same time, they differ in terms of solutions that can be proposed. Guillerme, Camille, myself, and Demir will start with commercial businesses, and we will explain you the challenges to decarbonize this sector, as well as the particular importance of electricity and efficiency here. Then, Baptiste, Arantxa, Milos, Alima, and Clara will introduce you to strategies, technologies, and policies that are of interest for the industry.
So thanks for the intro, Damien. So my project will be talking about the commercial side and economics for the commercial business, focusing on the raising energy awareness of dynamic UK electricity prices. So giving a quick background of how is the current situation of this commercial business, they are facing rising electricity prices. They are being required to engage with the energy market to meet the government's sustainable targets, and also they have a complex billing structure. However, most of this business lack the awareness of these things and can make straightforward decisions about their electricity management. Explaining more about how the commercial bill is composed, the figure on the right shows the three main components: the commodity, the environmental obligations, and the network charges. This last one considers the transmission, distribution, and operation costs of these components. These components, they vary depending on the spatial and temporal variations. For example, depending on the voltage level, where the consumer is located, and also the type of contract that these consumers negotiate. So with the aim to inform this business so they can make better informed decisions, my project was divided into three main processes. The first one, a model was developed to generate regional half-day hour electricity prices for this business. Secondly, I developed case studies with different business in the London area. And lastly, a website was developed to engage with stakeholders to gather their feedback to understand the main barriers and opportunities to engage the small and medium enterprises. So considering their demand and their electricity prices data combined, it was possible to analyze and gather some interesting insights from these results. The figure on the left-hand side shows how a daily variation from a food factory in London can vary. The blue line shows the summer weekday, and the green one shows the winter. It's possible to see that this spike increase of the prices is due to some of the network charger components that have higher prices during these peak hours. So this shows the importance to know how the prices vary during the day to avoid higher costs. Now, analyzing the evolution of the total cost from 2017 up to 2023, the figure on the right shows this cost for a London bar and how these components proportion vary throughout these years. The main insight from there is that these prices are expected to increase compared to the 2017 level. Now on the engagement side, it was developed a website that explained how this bill was composed, how these prices varied, and also provided the data for the users to engage with and raise their energy awareness. Through the feedback that I got from the stakeholders, main barriers were found. For instance, the lack of time that this business has to focus on this topic. Also, they have a small staff that is not aware of how these prices vary. And lastly, they don't know how to apply this data for themselves. So to overcome this barrier, main recommendations were found. So the website content should be succinct, should be attractive, and have tangible actions for them to apply. And lastly, it should focus on the financial and sustainable benefits from this business to engage with smarter management actions. So going on to the conclusions, the electricity prices were found, they're expected to increase up to 20%, comparing all the business cases that were conducted from the years from 2017 up to 2023. So this can be seen as a risk for the economical competitiveness of this business, but also as a motivation for them to become more energy aware. Regarding the SME sector, it was found to be that they are a difficult sector to engage, but as they represent 99% of the UK commercial business, they will be essential for the energy transition. And lastly, this data that was generated could serve as input for investment evaluations and also energy management optimization. So the main message from the project is that by becoming more energy aware, this business will be able to make the necessary and cost-effective investment to support the energy transition. Now Camille is going to present about a project of optimization.
Thank you, Guilherme. So the research topic I am presenting today aims at enhancing existing HVAC, which means heating, ventilation, and air conditioning systems in commercial buildings. The focus is put on the opportunities offered by the IoT and the cloud. But first of all, my guess is that some of you are wondering, what is HVAC? So HVAC is the system responsible for indoor condition management in buildings, such as the temperature, humidity, and CO2. It was of particular interest during COVID, for example, where the ventilation was essential to prevent airborne transmission of the virus. It represents 40% of the energy used in commercial buildings in the UK and differs from residential systems by its large scale and centralized structure. In this context, research has focused on enhancing the control of HVAC, usually regulated by a temperature-driven PI controller, either by reducing primary energy cost or carbon intensity or energy use. It includes techniques such as machine learning or optimization, which differ in terms of the amount and quality of historical data required beforehand, as well as computing times. If the performance of such method has been demonstrated multiple times, with savings ranging from 5% to 70%, it was mainly via simulation, resulting in a low uptake in the commercial sector. Indeed, lack of real-world demonstration, challenges related to the architecture installation, and lack of cost-benefits analysis have been identified as the main challenges to further bridge the gap between the literature and the commercial sector. In this context, the emergence of the Internet of Things and the cloud offers new solutions to implement these strategies. Firstly, IoT devices are able to communicate with heterogeneous components and collect data, useful when looking at retrofitting existing systems with a low upfront cost. Secondly, the cloud has the ability to centralize and store a large amount of data from multiple sources. In this context, a flexible model predictive control, which is an optimization framework, was developed to retrofit legacy HVAC system. Its uniqueness lies in the fact that it requires solely 2 months' worth of historical data. This advanced technique uses a semi-parametric model for temperature prediction and solves an optimization problem on the 24-hour horizon at a 30-minute time step. The goal is to find the optimal temperature set point to send to the legacy controller. As such, it uses electricity prices, carbon intensity, and outside temperature forecast to do this. The purpose of this strategy is to be easily applied to any commercial buildings. A case study was conducted on a large-scale supermarket in the UK, equipped with an IoT and cloud architecture, thanks to an Imperial project. A thermal network model was used as a simulation environment to replicate the behavior of the building and compare the strategies. Afterwards, a detailed cost-benefit analysis was conducted to inform commercial actors on the risk and benefits of such a project. 2 objectives were tested on the model predictive control. The first one being economic, looking at minimizing monetary cost, while the second one was looking at minimizing the carbon intensity of the primary electricity used. Both strategies result in overall better space temperature management and try to avoid peak prices or carbon peak. To give an order of magnitude, both cost and carbon savings are around 9%. Furthermore, this preliminary scheme had an interesting payback period, estimated at around 6 years, whose sensitivity to capital expenditure and savings has been studied. Key takeaways include that reducing the capex by 30% is possible by improving the communication on the project and gaining experience. It will result in a payback period divided by 2, so from 6 years to 3 years. Additionally, the payback period is also really sensitive to the efficiency of the central heating plant and hence the actual savings. The trade-off between retrofitting the existing HVAC system and upgrading the plant has to be considered. I hope this project helps you to understand how IoT and the cloud allow to further bridge the gap between research and real-world implementation of smart strategies. And now Damien will present to you how to use computing to further improve systems operation in commercial applications.
Yes, thank you. So Camille just explained how IoT and retrofitting can be very interesting to unlock savings and reduce CO2 emissions. And I am now about to present another important use of computational tools. The point will be to show that they can and that they must be used to better understand and control the systems that already exist, notably when they are complex and imply several pieces of equipment. So today, there is a rise of decentralized energy systems, often built around industrial or commercial buildings, and they can combine, for example, renewable energy, battery storage, electric vehicle for the employee, and connection to the heating of some offices, as well as a connection to the grid. In the UK, the national grid forecasts a high uptake of such system by 2050. But there is a lack of knowledge for the stakeholders that are using these systems. Indeed, they usually don't really know how to control it optimally or where to invest in priority. Sometimes also the question can be what are the benefits in terms of savings or in terms of CO2 emission mitigations. So a solution is to provide them with the computational tools that they can so that they can understand their system better and forecast its behavior and decide on the optimal control strategy to use. So for example, I've been developing a software that simulates all the fluxes between the different elements of such a system. And on the graph below, you can see here on yellow that we have a system with solar production. The electric demand is plotted in red. The energy imports from the grid is the dark blue lines. And you can see in green a battery that is being charged and discharged. With good inputs, such as forecast of the price of electricity, like told previously by Guillaume, the software can provide the user with a precise forecast of how the system will behave half-hourly in the next few weeks. And the tool was applied to the case study of a waste plant in Swindon, a city in the southwest of England. Thanks to the forecast of electricity prices and solar generation, it was possible to find a control strategy that generates savings and CO2 mitigation at the same time. So by avoiding price peaks that you can see on the left-hand side graph and using as much solar energy as possible, thanks to a smart control of the equipment, it was found that financial savings of 29% and CO2 mitigation of almost 20% were possible. And this just by changing how to control the equipment. So for example, when you decide when to buy the electricity, when to charge the battery, or if you have to turn on some machine at some times. And so it doesn't require any retrofit or new equipment to be installed. Moreover, this same software, thanks to it, it was possible to model the degradation of the battery on the site. And it was found that using the battery at full capacity will lead to very rapid degradation of it, actually in only 5 months. And so it was then possible to adjust the charging and discharging pattern to protect the battery. And thanks to it, the battery, without this new pattern of charging and discharging, the battery would have been degraded quickly, resulting in a loss of money because of a battery being useless and in an unnecessary pollution due to the battery production. So this is a small insight of the capacities of the software, but it shows that understanding the system that already exists is a priority to get better energy performances. Because they can be applied as of today, soft software and optimizations are tools that must be installed now. Now that Guillermo, Camille, and myself have focused on electricity as a vector of change, Demir will tell you more about the importance of fuel switching for commercial buildings.
Thank you, Damien. In the journey to net zero, many commercial consumers will face a challenge of covering their energy demand in a cost-efficient and environmentally friendly way. A part of that equation is a combined heat and power installations that historically allowed to produce required electricity and heat with reduced fuel costs and reduced environmental footprint. However, the latter statement is being questioned lately. To understand the challenge, let's compare the economic and environmental performance of CHP with business as usual solutions in 2010 and 2020. Business as usual case is represented by boilers for heating and electricity imported from the grid. So from the emissions perspective, in 2010, CHP shows 29% reduction in emissions versus the baseline, but in 2020, the reduction narrowed down just to 1%. With the electric grid set for further decarbonization, the future of CHP in this aspect is under the question. However, economic benefits or fuel cost savings of CHP increased from 37% in 2010 to 61% in 2020 due to a wider spark spread or the price difference between electricity and natural gas on kilowatt-hour basis. So it also may suggest that it would be profitable, extremely profitable, to run fossil fuel-based CHPs for as long as possible. On the other hand, the limiting factors are emerging for the businesses as well, such as increasing carbon costs, reputational risks, and tighter reporting and compliance requirements. These may drive businesses to start asking questions like, would a gas CHP be a sustainable solution in the future? Should we transition to an alternative energy solutions? And when that transition should happen? In trying to answer these questions, we have analyzed the case of a large food retailer who has a gas-fired CHP. Based on real-world data, we have built a simulation model with various scenarios to cover the energy demand of a distribution depot. So the model requires inputs such as technology capacities, energy consumption profiles, learning curves, market data, economic forecasts, predicted emissions intensities, combining all together. A modeling framework also includes various fuels such as hydrogen, natural gas, and energy technologies such as boilers, fuel cells, internal combustion engines to enable the direct comparison. And the results of modeling allow us to outline the future energy cost and its components throughout 2050. It also allows to perform sensitivity analysis for the most important cost factors, assess heat utilization impacts, and identify an optimal transition time. The findings of the research imply the following. So CHPs are poised to be less profitable in the future. However, they may have a significant role in certain conditions and applications. First of all, in case of favorable spark spread. So for that, hydrogen price should be heavily subsidized. However, the returns won't be matched to the ones of a natural gas CHP. Secondly, CHP can reveal its full potential in an application with high and constant heat load. This is where CHP's fuel efficiency will shine brightly and the hydrogen may be utilized in the most efficient way. Energy security and independence from the grid may be deciding factor for some users as well. In terms of switching CHP to hydrogen fuel, it's technically possible but economically challenging. Storage requirement for hydrogen alone results in £3 million investments. That fact also underlines the importance and urgency of a hydrogen pipeline delivery to commercial consumers. Otherwise, the hydrogen scenarios are not that feasible. Carbon prices are essential in transitioning to low carbon fuels, as in a central scenario in modeling, gas-fired CHP will no longer be feasible by 2035, mainly due to carbon costs. Okay, next we will move from commercial sector to industrial decarbonization, and my colleague Baptiste will outline the challenges of this complex topic.
Thank you, Demir. Okay, so let's take a short break in our presentations to state clearly where we are. So far, Guilherme, Camille, and Damien have highlighted solutions to optimize the energy use in commercial buildings to reduce both the costs and the carbon emissions. So it's already possible to make the most of these opportunities now. Then Demir focused on a transition to more deeply decarbonizing solutions with the use of CHP and hydrogen in commercial buildings. So this second type of solutions might not be fully ready yet, but it will be absolutely necessary to meet the net zero targets. What we are about to show now is that this story is also valid for the second part of what the UK government calls the business sector, namely industrial activities. Industry is really a key sector if we want to meet the net zero target. First, because it is usually quite energy intensive. And obviously, for this reason, industrial emissions represent a big share of total emissions. And second, because industry is actually not just about industry, because industry manufactures the technological solutions that will help decarbonizing other sectors of the economy, like transport, like the domestic sector, for instance. So decarbonizing industry is pivotal to decarbonize the entire economy. In 2020, the Climate Change Committee advocated that industrial emissions need to be cut by 90% by 2040 from 2018 levels if the net zero target is to be met. So for this, many solutions already exist. For instance, energy efficiency measures that have been responsible for most of emissions abatement in the last decades can still be pushed further. But as we have just seen with commercial buildings, they won't be enough, because usually energy efficiency can abate emissions by 10, 20, maybe 30 or 40%. But in any case, we will always fall short on the targets. So more deeply decarbonizing solutions are needed. Among them, lower carbon fuels like biomass, biogas, hydrogen, or also carbon capture and storage plants that can be used to capture remaining emissions after combustion. The following presentations will address how to pave the way for these different solutions. But first, I would like to present you what can be done in the medium term with these technologies to start decarbonizing industry at a relatively low cost. Low carbon fuels like biogas or hydrogen, but also capture technologies that represent a great opportunity for industry decarbonizations. But the problem is that the adoption of these technologies in industry is currently close to zero because of some remaining barriers. The high operating cost and the prohibitive upfront investment required, sometimes the low technical and environmental readiness of these solutions, and also the lack of adequate infrastructures. What I'd like to show you with this research is that it's possible to achieve a deep decarbonization of industrial energy systems at low mitigation cost by combining hierarchically abatement strategies. So for this project, I considered 4 industrial abatement strategies. First, energy demand reduction from the processes implemented through heat integration. Second, an increase in the supply efficiency of energy systems through waste heat recovery. Third, fuel switching to blue or green hydrogen, but also to biogas or to electricity. And finally, carbon capture and storage. I physically modeled all these strategies with the different combinations on 2 typologies of industrial energy systems, a heat-only system and a combined heat and power, which means that in total 54 decarbonization scenarios were designed. For each scenario, I then calculated yearly greenhouse gas emissions and annual costs, and I used them to determine the abatement potential and the mitigation cost effectiveness of each combination. So here I displayed the results of this analysis for the heat-only system in a marginal abatement cost curve that represents both the abatement potential of the different scenarios on the x-axis and the marginal cost of abating 1 ton of CO2 on the y-axis. Each of these boxes is a scenario. When a box is above the axis, the scenario comes at a net cost for the system, and when the box is below, the scenario is cost saving. Also, the wider the box, the more decarbonizing. So what does this graph tells us? For a heat-only energy system initially running on natural gas, energy efficiency strategies, so the blue boxes on the left, are economically viable, but they are not enough to cut emissions. In contrast, more deeply decarbonizing solutions like fuel switching or CCS, so the green boxes on the right, are too costly to become credible solutions. But hierarchical combinations, which are in the middle, allow to reach high decarbonization rates while also reducing the mitigation cost. So for instance, an 89.3% cut in emissions can be achieved while also decreasing the system cost. What happens here is that energy efficiency measures are usually associated with low upfront investments. They are easy to implement and they are cost saving. So they can be used first while optimizing the system to reduce the energy consumption, to decrease the cost, and to further invest in costly abatement measures. So in the end, I found that the optimal hierarchy of strategies is 1, demand reduction, 2, supply efficiency increase, 3, fuel substitution by hydrogen or biogas, and 4, CCS. Now for a CHP system. So less opportunities for decarbonization exists because the system is already more efficient. As you can see on the graph, no significant abatement is cost saving for the system, which means that policy intervention will be required to incentivize decarbonization. But the overall conclusion remains similar. Hierarchical combinations are interesting because they reduce the level of policy needed. For example, a carbon price of only 17.6 pounds per ton of CO2 can support a deep, cost-effective decarbonizations, cutting more than 86% of initial emissions. Overall conclusion, combining hierarchically abatement strategies does reduce the mitigation cost and does make a deep decarbonization viable. After discussing costs, I would like to hand over to Arantxa, who will address another barrier to deeply decarbonizing solutions, that is the low environmental and technology readiness in the specific case of hydrogen.
Okay, thank you, Baptiste. Now, indeed, I will talk specifically about green hydrogen and the potential it has to decarbonize an industrial cluster. Hydrogen can be produced by different methods, codified by different colors, each associated with a range of emissions and cost implications. Most of the hydrogen is produced via steam methane reforming, releasing CO2, which is known as gray hydrogen. Carbon capture and storage can be included to reduce greenhouse gases, which is known as blue hydrogen. However, the CO2 storage opportunities and the fugitive methane emissions have to be contemplated. So, from an environmental point of view, green hydrogen could be the best option. Furthermore, green hydrogen can be produced by different types of electrolyzers, with the growing importance of alkaline water electrolyzers. So I have performed a life cycle assessment to quantify the environmental burdens associated with two designs of alkaline electrolyzers to evaluate how green this technology actually is. The electrolyzer is evaluated from cradle to gate, from the mining and extraction of the raw materials to produce one stack to the production of 1 kilogram of hydrogen. The scope of this study includes the manufacturing phase, the operation phase, and finally the combined system. When considering the operation and the manufacture phase combined, it can be seen that the operation phase contributes the most to all the impact categories. Within the operation phase, it was found that electricity contributes to more than 99.8% for all the impact categories. For the manufacturing phase, nickel, as shown in the yellow circle, represents environmental hotspots due to its high emission factor. It is important to consider what materials have the most impact, especially when evaluating the uptake of this technology in the future. Furthermore, a case study is devised to set decarbonization pathways for a cluster in Spain over time, from 2020 to 2050, considering the Spanish hydrogen roadmap targets, which are a maximum of 6 megawatts of green hydrogen installed capacity by 2024 and 4 gigawatts by 2030. After this date, there isn't any established targets yet. So the cluster is located in the south of Spain and is formed by 19 industries, of which 4 are further evaluated, which are 2 combined cycle plants, a fertilizer plant, and a hydrogen production plant. The technologies considered are gray, blue, and green hydrogen production methods. So 3 scenarios are evaluated, considering the different hydrogen production technologies and electricity supply options. Scenario 1 considers the business as usual, hence an electricity supply from the grid is evaluated. Scenario 2 is aligned with the installed capacity proposed by the Spanish hydrogen roadmap, so we can see an increase in the capacity installed 5 years before 2030, which is the red arrow. Lastly, scenario 3 is aligned with the hydrogen roadmap and considers an all-renewable electricity supply option, hence representing the most optimistic scenario. The results show that if an early uptake by 2025 of the installed capacity is considered as proposed in scenario 2, which is the green line, the environmental footprint in that period increases. This is because an early uptake will imply an electricity consumption with a higher emission factor compared to 2030. Scenario 3, which is in the gray line, shows that Spain could align with the hydrogen roadmap if a renewable electricity supply is investigated, if a renewable electricity supply if an all-renewable electricity supply is investigated due to its lower emission factor. So this case study shows that the electricity supply contributes the most and influences the real trade-off of emissions in the system. This study was based in the technological readiness level of these technologies and considers the environmental footprint only. However, economic and social impacts should also be studied to facilitate the best decision making. Now, Milos will explain how to make the commercialization of this technology feasible.
Thank you, Arantxa. Indeed, this project focused on constructing a cost-effective pathway for the increase of hydrogen's market share in the UK chemicals sector via the implementation of policy interventions. Although the TRL of hydrogen-ready industrial devices is high and the environmental benefits of fuel switching to hydrogen use is clear, market adoption is essentially non-existent. The key barrier is financial, as hydrogen is at least 6 times as expensive as natural gas. To induce commercialization, this barrier must be alleviated, and was done by applying a constructive policy in the form of renewable incentives and a destructive policy in the form of a carbon tax. Lastly, the effect of hydrogen price reduction as demand increased was also analyzed. Initially, the 2 aforementioned individual policies were implemented. Next, the policies were combined and applied simultaneously. When applied individually, a single policy caused the full cost burden to fall on either government or industry. However, when it was applied together, they could be adjusted to split the cost evenly between the 2. For green hydrogen, this led to a 50% savings for government compared to the individual destructive policy, and 56% savings for industry compared to the individual constructive policy. It also showcased that switching now to green hydrogen is more than twice as expensive as to blue hydrogen. The increase of market share leads to an increase in demand volumes for hydrogen. This means that more hydrogen must be produced and its price decreases due to the learning rate. Blue hydrogen's learning rate is much lower compared to green hydrogen as it is more mature, so its effect is much smaller. Currently, green hydrogen is far more expensive than blue hydrogen. However, with a demand increase, this situation changes. At just 7 terawatt-hours of extra demand, the prices equalize, and with each additional demand increase, green hydrogen becomes increasingly cheaper than blue. By 100% market uptake and almost 23 terawatt-hours of increased demand, green hydrogen price is almost £1,000 per tonne, whilst blue hydrogen is £1,500 per tonne. From this, 2 pathways were created that either increased the market share incrementally in a stepwise fashion over 7 years, or directly to 100% uptake in 1 year. The time taken to reach 100% had an effect on the cost. By incrementally increasing market share, the cumulative cost after 8 years was 38% lower for green hydrogen than the direct pathway. Most importantly, however, by including the hydrogen price development, it was now seen to be more cost-effective in the long term to transition to green hydrogen. However, using green hydrogen throughout led to high costs early on, as the green hydrogen price is so high. To mitigate this, a final stepwise pathway is formed that integrated the use of both hydrogen types. Blue hydrogen was used to kickstart uptake until the 7 terawatt-hour crossover point was reached. After this, in year 3, the switch was made to green hydrogen as its price was now lower. Due to this, the previous stepwise green hydrogen pathway cost was reduced by an additional 11%. However, when all the policies were removed in year 8, market share fell to 0% once again, as the price reduction had not been enough and policies were still needed. For the 100% uptake to be maintained while all policies are phased out, the hydrogen price would have to drop to under £600 per tonne. To reach this, an additional 122 terawatt-hours of demand for green hydrogen is needed. As this cannot be obtained from this market, it would have to be generated from other sectors for hydrogen fuel switching to be market-driven. Thus, it can be seen that to create the most cost-effective pathway for hydrogen fuel switching, policy should be combined, market share should be increased in steps, and blue and green hydrogen should both play a role. Halima will now show a similar methodology framework can be applied to commercialize the use of CCS.
Thank you, Miloš. In addition to hydrogen boilers and CHP, carbon capture and storage is necessary for deep decarbonization of industry, mainly because of energy-intensive processes that are hard to decarbonize, like iron and steel making. However, the high cost of capture incurred with the implementation of CCS is a huge barrier to adoption. And so I'm going to be highlighting the impact of policies and business models on increasing the adoption of CCS in a market and reducing cost of capture. A quantitative approach in the analysis of the role that policies, business models, and the size of a market will play in increasing the market share of a technology and reducing cost of capture has been taken for several types of CCS technologies applicable to the iron and steel industry. and this was applied to a global case study of all the integrated steel plants in the world. The market was defined based on the amount of CO2 emissions from these plants, as well as the percentage of these emissions capturable with CCS in a plant based on the technology type. The results from the analysis showed that existing interventions in the form of policies like grants, carbon tax, emissions trading scheme, and a business model that exists in the form of carbon dioxide sales for enhanced oil recovery are not enough to make carbon capture seem attractive enough to cause a good increase in the market share of CCS technologies in the iron and steel industry, or reduce the cost of capture based on the CCS learning rate. Therefore, improvements to these interventions are required. For example, in the case study presented, the gray area represents the market share attainable with existing interventions. And out of the maximum of 50% emissions capturable in the market with this CCS technology shown on the market share axis, we can only go from 0% adoption in the baseline, which is where we are today in the iron and steel industry, to about 2.6% at most with existing grants. This is significantly low and has no impact on reducing cost of capture. The learning rate for CCS was observed to be quite slow, which means that very little knowledge is gained as global capture capacity increases. Based on a cost reduction potential assessment performed, achieving an immense reduction in cost of capture of a CCS technology type would require the complete adoption of the technology in a given market. By improving the interventions to create a demand that can push CCS into all integrated steel plants, cost reductions between 27.9% and 50.4% can be achieved for various CCS technologies, depending on their initial cost of capture and capture rate. Maximum adoption in a market can be achieved by either choosing to improve and implement a single intervention or by optimally combining multiple interventions. However, with the combined mode, it is possible to split the burden of costs between government, industry, and the buyers of CO2, for example, using a combination of grants, carbon tax, and a business model for revenue generation. This ensures that the burdens to government, industry, and the buyers of CO2 are significantly lower compared to if either of them was to be responsible for a single incentive to push for maximum adoption. And so the combined mode allows for a more cost-effective transition and is therefore recommended as the best pathway. The quantity of interventions required to increase uptake in the market has also been found to reduce after cost of capture falls. Based on all the findings in the research, it is essential that the existing interventions are reformulated and implemented immediately to prevent delays in increasing market adoption and attaining cost reductions. This means that by pushing CCS into all plants in a given market, in this case, the iron and steel market, the cost can reduce significantly, thereby creating opportunities for cost-effective adoption of the technology in all other hard-to-abate sectors throughout industry, with the aim of meeting targets set out for 2050. Now that we have explored the different technologies that will likely play a role in the future of industrial decarbonization and measures to commercialize them, Clara will talk about the modeling of the infrastructure required to facilitate their on-site implementation.
Thank you, Halima. So although there is a comprehensive understanding regarding the technologies which will likely play a role in industrial decarbonization, as the previous presentations have illustrated, little has been done with respect to the explicit modeling of processes and their evolution in the clean energy transition. The aim of this project was a proof of concept for modeling these industrial processes and decarbonization options based on publicly available data and a focus on modeling infrastructure requirements for both hydrogen and carbon. Additionally, analyses were conducted regarding the interdependencies of different decarbonization technologies and fuels. To effectively model the decarbonization of industry, UK industrial processes were characterized using data on the magnitude and location of the energy demands, emissions data, fuel efficiencies, and nameplate capacities. To model decarbonization options, data on costs and percent CO2 reductions from the UK government were used. The project focused on the three highest emitting industrial sectors in the UK: iron and steel, oil refining, and chemicals. The technologies for hydrogen generation included water electrolysis, biomass gasification, as well as ultra-thermal and steam methane reforming technologies. In the initial analysis, increasingly stringent carbon emission constraints were applied to the system from 0 to 100%. This graph shows the breakdown of where system emissions originate. Between 0 and 10%, the greatest proportional decrease is observed from the industrial sector, almost maximizing its full potential as not all processes were given the option to decarbonize. This is followed by increasingly higher emissions reductions in both the domestic and commercial sector through hydrogen boiler substitution. At 50%, biomass becomes a cost-effective method for removing carbon dioxide from the system alongside CCS, and gross emissions stop decreasing while an increasing amount of biomass gets introduced to the system. The modeling results are used to visualize the infrastructure requirements. The figure on the left shows the system at a 10% CO2 reduction, while on the right, the system is shown at net zero. At 10%, only one offshore site is accessed for storage, with an extensive onshore CO2 network, shown in dark blue, while the development of a hydrogen network is minimal. In contrast, at 100%, all 3 offshore sites are being used to store CO2, resulting in a much smaller onshore carbon network, while an extensive hydrogen infrastructure is shown in purple. From this, it can be seen that the infrastructure for short and long-term decarbonization don't necessarily align, and hence a better understanding of what the system might look like under different scenarios is essential for informed policymaking today. To further investigate interdependencies of carbon abatement methods, 2 biomass scenarios were developed, one limiting its availability and a second increasing its cost. These scenarios were used to analyze how the system would react if the negative emissions associated with the use of biomass were constrained. As can be seen on the left graph, increasing the cost of biomass results in a later introduction of the fuel at 80% rather than 50%, as is the case in the initial scenario shown in black, with hydrogen and CCS being the more attractive option. As a consequence, the system cost increases significantly, as can be seen in the bar plot on the right. To further illustrate this difference, the system infrastructure at a 70% reduction is shown. The system on the left has no biomass constraints, while the right one depicts a system with an increased biomass cost. In the initial case, on the left, the hydrogen network is much less developed across the country. An increased cost of biomass causes more decarbonization options to be deployed at industrial sites, and more extensive offshore CO2 pipelines are developed as more carbon is stored overall, as the sites use an increased amount of CCS. This further highlights the extent of interdependencies between different decarbonization technologies. The main conclusions drawn from this research are that a dependency on both fossil fuels and biomass at net zero seems inevitable. There appears to be no way for the system to reach 100% emissions reductions with solely CCS as a means of removing emissions from the atmosphere. CCS was found to be more cost optimal than biomass, and the development of carbon infrastructure takes priority over hydrogen infrastructure at lower emissions targets. It was found to be more cost-effective to focus on the reduction of large point source emissions associated with energy-intensive industries, as opposed to the much more distributed, smaller domestic and commercial demands. This also highlights the importance of industrial clusters for the clean energy transition. While early action with respect to industrial decarbonization and the associated infrastructure developments required is vital, this is not necessarily reflected by the current policies due to the threat of carbon leakage.
Thank you, Clara. So to summarize, the decarbonization of the commercial and industrial space will prove to be a massive challenge in the future. However, to facilitate a smooth and cost-effective transition of these energy systems, early action is vital and policy intervention is critical. Though the opportunities regarding the technology and system which will be integral to the clean energy transition are understood, as presented today, the way in which this might be realized remains unclear. In the commercial sector, decarbonization will go hand in hand with smart management of energy consumptions, which will ultimately lead to both cost and emissions reduction due to increased flexibility for the electricity grid. As discussed earlier, due to the higher cost of decarbonizing industry for hydrogen and CCS, policy intervention is pivotal. The current state of policy intervention is found lacking, and extensive collaboration between industry and government is required. A successful energy system transition for commercial businesses and energy-intensive industry will require a whole system approach to achieve net zero. In that context, all the above presented projects highlight research gaps for which further study is needed to improve informed decision-making. Thank you for your attention and happy to take any questions.
Thank you, guys, for a very interesting presentation. We should go straight into questions. I can see there's a few questions on the chat. So I'll hand over now to Piotr Konopka, who's a Senior Manager for Energy and Decarbonisation Programmes at DP World. Over to you, Piotr.
Thank you very much. Thank you to all the students, first of all, for the very insightful presentations, and congratulations on being just a couple of hours away from this milestone of completing your courses. Of course, thank you to all the staff at Imperial and supervisors, and a warm welcome to everybody else dialing in. As a very brief intro, my name is Piotr Konopka. I've actually graduated from the SEF course back in 2014. And following a few years in strategy consulting, I'm currently working at DP World as a senior manager for energy and decarbonization programs. And whereas the energy industry has seen a ton of innovation, can-do attitude, a lot of fresh thinking, I strongly believe that this topic that we'll be discussing, right, how can legacy industries fit into the energy transition, is very, very important. DP World being a shipping, logistics, and ports and terminals operator, there is a lot to do, and the things that we've heard about today are all very relevant. I've heard four main themes today. One is hydrogen that Aranza and Miłosz talked about. I think Miłosz put it very well that we are there when it comes to technology readiness level, but we're probably just right now at the brink of a big hydrogen transition, given where the policies are heading. Then we had Camille, Clara, and Demir talking about heating. I think in the energy transition over the past 10 or 20 years, electricity has been getting a lot of attention, but heating definitely is a big problem. I think as also rightly highlighted in the keynote speech by Stephen. The third theme I've heard today is you cannot transition legacy industries with legacy methods. And this topic of smart and digital is very, very important in that transition. And then last but not least, Halima and Baptiste talk about pathways and roadmaps. You cannot just take a technology and run with it. You need a solid roadmap aligned with stakeholders really to make it happen. So you've mentioned that there are some questions already. So I don't know how you want to do it. Do you want to read them out and direct them at the students?
No, actually, Piotr, are you able to look at the Q&A chat? If you click on the.
Okay, it's opening.
Yeah, you can just ask it to you. Yeah.
Fantastic. Okay, so the first question that I see here is, which just it's published now. Okay. It's just disappeared from my screen. There was, yeah. So to achieve a net zero target, could you please elaborate again on what your team conclude around the CCS infrastructure and the hydrogen infrastructures? Maybe first talking about CCS, Halima, what's your view on that?
Thank you for that interesting question. So as I mentioned, CCS is crucial in the journey to attaining net zero. And so in order to promote wide-scale adoption, it is essential to reduce the cost of capture. And from my findings, to do that, CCS has to be pushed into a given market, for example, the iron and steel market. In doing so, significant cost reductions can be attained as global capture capacity increases. What this means is sectors in industry that are currently difficult to decarbonize can have the option of capturing their emissions. And also, when you look at developing countries which are still highly reliant on fossil fuels, CCS has a crucial role to play in that. So by reducing the cost of capture and making the technology affordable, then significant decarbonization can occur globally. So that's what I have to say.
Thank you, Halima. It's very insightful. The second part of that question was about hydrogen and hydrogen infrastructure and its vitality in achieving the global net zero targets. Aranza, what do you think about that?
Can you hear me?
Yes.
Okay. Yes. I mean, my project is more centered in the hydrogen production in itself, not the infrastructure. But I believe that is essential, but I think more research should be done, especially in the hydrogen storage, since there are a few, if we are talking about long-term and big capacity of hydrogen storage, there are only a few projects only right now. I think was one in the US and another in the UK that are developing this technology. So if we're thinking of a big uptake of hydrogen capacity installed, we have to think also about where are we going to store it. So I think infrastructure, considering hydrogen, that should be a key point to look at, because in terms of transport, it cannot, we are even considering sometimes blending it with natural gas in the current infrastructure. So without any big investments, if we consider until a certain percentage of the mixture of the blending. So I think a key focus right now could be in the storage. Thank you.
Great. Thank you. And sticking with the topic of hydrogen, Miłosz, there are a few questions actually I see directed at you. One is, if you rely on blue hydrogen to increase demand in short term, what happens to production capacity that is installed to meet this demand after it is no longer cost effective compared to green hydrogen?
If it's ever on mute.
I can hear you well. Oh, you're back on mute.
Okay, right. Yeah. Hi, everyone. That is actually a great question. This was at the end of my research, and it was an idea to try to bring together the two pathways. And I had the exact same issue in terms of now we're going to have obsolete production capacity of blue hydrogen that seemingly doesn't have a role. So for two reasons, I initiated this sort of proposal. The first was that, you know, without it, green hydrogen, demand for green hydrogen would never be instigated, so you would sort of need it to kickstart. However, the research showed that the production capacity was only 7 terawatt hours of blue hydrogen, which on the grand scheme of things is relatively negligible. But of course, there is a question whether the individual producers of that blue hydrogen would have confidence to do that. And I think, to be honest, the main thing needed is really clear guidance from the government that this transition is to take place. I think that, you know, communication would be key to make sure that everybody is on the same page. And my study focused solely on not only industry, but more specifically on the chemical sector within that industry, which means that blue hydrogen could be used as, again, a transition fuel for all the other sectors, not only iron and steel, as Halima was pointing out, but also transport, residential. And I think with time, you would see more uses for it. And I think also the government would have to dictate that once it became obsolete, so to say, they would take care of that, because it's for the government's benefit that these producers would set up, let's say, one other production facility and then take that. And then you could maybe even export that blue hydrogen later on. I mean, all of Europe is now starting to try to transition to hydrogen. So I don't think it would be that much of an issue to find demand for 7 terawatt hours of blue hydrogen, but definitely communication would be key.
Excellent point. Thank you, Miłosz. We have a question from Faye to Camille and Damien. So Faye is wondering how important the forecasting is for your work. Have you quantified the impact of good or poor forecasting on the benefit of the proposed methods? Camille, if you want to take that first.
Sure. So for me, forecasting is really key because it's the key thing that helps to predict the building temperature in my case. And so it's like the whole strategy relies on forecasting. And so I think there's two sides. The first one is like the length of forecast that is needed. Is it like 24 hours or 10 hours? And I try to quantify that. And like, it's kind of similar in my case because of the thermal inertia of the building. Having 10 hours horizon or 24 hours horizon is kind of similar, although 24 hours is better. That's why I chose it. And also because of the really slow inertia of the building, I mean, it's the robustness of the algorithm compared to forecast is kind of like embedded in the algorithm. However, I think it would be interesting to look into like the how robust is the strategy, like regarding the robustness of the algorithm compared to the forecast, but also to the quality of the data that is collected inside the store. So I think it would be like it's actually in my next steps in my thesis is looking at how to improve the algorithm to make it more robust, and it includes the forecasting.
Great.
And I think Damien can take on.
Yeah, just to thank you, Camille, and thanks for this very interesting question. So actually, same as Camille, in my project, like the forecasts are really key because they're actually the input of the software. So in the system I've been considering, I need to forecast the solar production, the grid CO2 intensity, the electric demand from the factory as well, and the electricity prices. But so in the actual version of the software, like the forecasts are really the inputs, and everything depends on that. To be honest, I have also tested a version of the algorithm working only with previous and present data. So for example, knowing the state of the battery right now and what's the electricity demand right now, how to make all of this work. But there are two things. First, to have good results, we would require a much higher data granularity. So I was working only with half hourly data, but with, for example, to work with present data and adjust to what's happening right now, I think we will require to work with data happening at a rate at less than 1 per minute. So we will need a much higher computational power. And of course, the result will be less precise. So this question actually highlights the very important stake for the future, which is the quality of the data we will have. And I think that in this field, artificial intelligence will have prime importance in the future. So this is definitely a technology that will need to be developed to sustain the energy and the smart transition for the future.
Excellent.
And
Thank you.
if I can add on to that, I think also like the development of the cloud, as I mentioned, so we have the ability to store a large amount of data that we can process. So as with machine learning, as Damien said, and so we have the ability to have to improve the forecast that we do and to have better data to use in the algorithm. So it's something that will probably be developed in the next few years, I think.
Great, thank you, Camille and Damien. We have another good question about carbon pricing in terms of how you think it can or should be used to align economic and environmental aspects, and even more crucially, what are the risks if we get the price wrong? So maybe let me direct this question at the group that focused on heating. So Demir, you talked about the role of combined heat and power in a net zero world. How do you think carbon pricing fits in that topic?
Yeah, I can add a couple of words about that. Well, yeah, one of the main outcomes of my research is that the carbon pricing is the main driver of a transition. For CHP, for the analyzed case, by 2040, around 40% of energy spendings will be carbon price. So, I mean, it suggests that without carbon price, running gas-fired CHP, will be more feasible than transition. So there will be no incentives to transition to low carbon fuels from end users' perspective. So they will not be incentivized. However, my research didn't take into account some benefits, like systematic benefits of CHP, such as it relieves the load from the grid. It also can participate in balancing and so on. So UK government incentivizes CHPs as it allows to cut the emissions compared to a separate production. So it suggests that my idea is that the carbon price should be tailored on sector-by-sector basis, because in case of CHP, I mean, these parameters should also be analyzed when pricing its emissions. For example, sectors like steel production, they are more prone, I mean, they're more ready for a transition from gas. So, and we see that the more developments to hydrogen in that area, steel and cement, these were the first sectors to be priced, I mean, transborder pricing as well. So, but other sectors, they're very susceptible for, maybe very susceptible for carbon because it has socio-economical impact. It will imply the higher cost for consumers. All these carbon prices will be priced in the all the products that we consume, and that was one of the results again. In the future, we will have higher costs irrespective of what technology we'll be using. So gas, fossil fuel technology will be carbon priced, but the lower carbon technologies, they are expensive on one hand, and they have higher OPEX on the other hand. So yes, I think that is very important to price it correctly in order not to boost the retail consumer prices as well.
Yeah, excellent. Thanks, Demir. I think you're raising a very good point around varying approach sector by sector. So let me ask the same question to Clara, since you've looked at decarbonization across different sectors, more from the infrastructure side, but how do you see carbon pricing fit in that?
So very interesting question. Since I didn't really focus on policy in my research, there's a limit to how much I can discuss this, but I did do a lot of research on the challenges of industrial decarbonization, specifically for energy intensive industries like the iron and steel, like the cement sector, like chemicals and oil refining. And the thing I kept seeing over and over again is that the reason nothing's really been done in recent years, no major policy implementations or carbon prices, is because there's a massive fear of carbon leakages. So if you impose the carbon tax, those companies might move their manufacturing to pollution havens where that tax might not exist because of the low marginal profits and the fierce international competition, especially for like sectors like iron and steel. And for them, it's just not worth it than keeping their manufacturing in the UK. So this is something that I think will provide a massive challenge in the future, because the government needs to find a way to reconcile those threats of carbon leakage with also incentivizing decarbonization in a way to make it financially viable for the companies.
Makes perfect sense. Thank you. The question to Baptiste, you talked about the abatement costs in industrial energy systems, kind of bringing it back to the question of this debate. You know, how can legacy industries fit in the energy transition? Which legacy industries do you think are the most problematic? You're on mute.
Actually, that's a very good question. I don't know if I would be the appropriate person to answer this because my thesis was not focused at all on some specific sectors. I tried to model a system that would be representative of most models like energy systems and steam systems, sorry. So I don't know if I would be able to go sector by sector. Yeah, this was not the focus at all of my thesis, so I didn't, I'm sorry. I couldn't go on details on this one.
Maybe you could,
go ahead, Clara.
Yeah, if I could just maybe contribute. Based on my research, one of the things that really stuck out to me is that a sector like the food and drink sector, which is highly distributed, almost like commercial and domestic heat demands, is going to be super challenging to decarbonize because no industrial clusters in the food and drink sector exist. While, for example, cement or iron and steel. Like in the UK, there's 2 integrated iron and steel works. And like if you want to decarbonize the iron and steel sectors, you have 2 geographic locations to focus on and to build your infrastructure around. But the food and drink sector is going to provide way more of a challenge in that regard.
Excellent. Miłosz, I see there's a lot of questions about hydrogen, a lot of them directed at you. I'm curious to hear your thoughts on, you looked at specifically the UK chemical sector. Do you think that the chemical sector should be kind of the first mover there, or you know, do you see many parallel sectors and parallel industries kind of working together to achieve that hydrogen hydrogen future?
Yeah. It was actually the first step of my research was to choose the market scope and choose one sector specifically. So I spent quite a bit of time perusing through 8 different sectors and trying to figure out which one would be most appropriate to switch to hydrogen. And I think the reason why I hit on the chemical sector is, you know, quite a bit of the companies already produce hydrogen on their site, even if as a byproduct, which means that the safety protocols that they have in place, the knowledge that they have about handling hydrogen is much greater than all the other sectors. And exactly like Clara was saying, the food and drink and the paper companies, the industries, they are far more distributed. And because of that, a lot of them actually are now starting to switch to biomass instead of hydrogen. They've already started to make that transition because they are, I mean, obviously, paper makes sense, right? Why they are using biomass to transition to decarbonize. But then food and drink, similarly, they're going to areas that are closer to forests, closer to places where they can get that alongside, obviously, you know, corn husks and everything. So all in all, I think that the chemical sector is actually the best to trial the start of hydrogen. But at the end of the day, if we are actually serious about decarbonizing and government wants to implement policies, then yeah, for sure, iron and steel and all the other ones, cement especially, should look into it, because they have such high heat demands, such high energy demands, that's the reason why hydrogen has to be. I saw a question below which was about which sector has the most demand, and it's not even the fact that industry has the highest demand for hydrogen, it's because it doesn't have as many alternatives. So just by virtue of that, it is the best sector to introduce hydrogen into.
Yeah, makes perfect sense. Thanks. Another question we have in the Q&A is around prosumers and, you know, a model for prosumers in a DER society who are sharing produced renewable energy and this societal use case that connects EVs, batteries, EV charge points operators. Guilherme, you've looked in your work, you've looked at the dynamic UK electricity prices. Maybe you're the best person to comment on this.
Yeah, actually, thanks for the question, but I think Damien will be the best person to answer, because I use just like the demand from the business, commercial business, and I think Damien looked more into this integration.
Yeah, absolutely. I will answer that question. But just quickly, if I have the time, I also would like to quickly talk about the carbon price that we have been talking about. So about the question of Faye and the good price of carbon. So my comment on this is that, you know, right now there is the emission trading system. So it puts the carbon price on the market. And I think actually it's a good solution, but also would like to raise awareness about regulation about that, because right now the ETS price is higher than ever, and we can see that with combined different external reasons, it can also lead to very high prices for the population. So for example, right now what we can see in Europe is that Russia is restraining the supply of gas because they want their Nord Stream 2 to be settled as quickly as possible. So the consequences for Europe population will be that they might pay about 1,000 euros additional in their bills for heating this winter. So just it shows that it's important to keep regulation about it, and that without any care of this carbon price, it can lead to, combined with others parameters, it can lead to things we don't control and price that can put the poorest people into even more energy poverty. So my comment just that the market approach is good because it doesn't need policy intervention, but still a regulation I believe is necessary, like for example the France electricity prices that are balanced year after year. So now about the question. So indeed the model that I built, in fact, the whole point of this model is that it can be adapted to any kind of structure. So the result that I've presented you is adapted to an industry case, but actually you can adapt it by changing the different inputs to a house connected to one electric vehicle and operating with only few solar panels instead of a whole solar farm like I have done. So if you want any more detail, maybe you can contact me to know about that, because all of this is available in my thesis. So I'll just drop my email address below your comment and just contact me if you need anything.
Excellent. Thanks for the invite. We only have 2 or 3 minutes left, so I was hoping we could round up this session with a very, very quick round table. So I was curious if each one of you, in literally 1 sentence, max 2 sentences, could specify what do you think is one biggest challenge and one biggest opportunity for legacy industries to fit into the global energy transition. So maybe let's go reverse order to the presentations. Clara, one challenge, one opportunity.
So I guess I already discussed the challenge earlier of carbon leakages. Just a way for the government to incentivize the decarbonization in the first place is going to be so much harder than I believe in the power or transport sectors. But one big opportunity are the development of infrastructures that will be accessible to all the other sectors. So if you're developing a hydrogen network for the transport sector, like it would be a massive opportunity for the industrial sector to switch to hydrogen as a fuel.
Excellent, thank you. Halima?
So for me, I think the biggest challenge right now is the insufficiency in policies pertaining to CCS adoption. In reformulating these policies, capture, which has a bigger impact than paying for emissions in the form of a carbon tax or emissions trading scheme, can be made possible. And so that's the opportunity with CCS. You get to capture emissions and contribute better to the global decarbonization framework than actually paying for emissions. So, yeah.
Great. Miłosz?
I think the biggest opportunity for this decarbonization to take place is that high technology readiness levels already exist for all the technologies that we need to be able to do that, meaning that the transition is possible. However, the challenge is directly linked to that, and it's quite simple. Money, just money. It's going to cost.
Arantxa?
Okay, so I think one of the biggest challenges is we have to assess the whole system from a systems perspective, and this is mainly a life cycle assessment. You just can't consider one process, because a lot of the times you associate the burdens with one process, and then you aren't considering the whole system, and there are burdens associated with one product in another country, for example, or in another process, but that end up the production of the main process, the main product. So I think we have to keep always that in mind when assessing like the technologies that are the best option for the future.
Thank you. What do you think, Baptiste?
Well, I think if we want to decarbonize deeply the industry, probably the greatest opportunity is that most solutions are already kind of well known. And the biggest challenge is that despite the fact that they are known, they are not adopted yet, which means that we still need to put a lot of efforts on incentivizing them and also raising awareness, because some of these solutions are already well developed, but just not adopted. So even just raising awareness would be a great step first.
Thanks. Demir, quick challenge, quick opportunity.
Yeah, as I mentioned before, the challenge I think are the rising fuel costs, rising energy costs for all kinds of users. On the other hand, it also shows an opportunity. It's in hybridization, in combination on different technologies and R&D as well. So we have to try to, legacy technologies try to combine existing technologies in a way that would decrease emissions and money as well, like spendings.
Thanks, Damien.
So very, very quickly, I think that challenges, of course, is to always keep a global approach. So as Clara said, to avoid carbon leakage. And opportunity as well is the raising awareness. People now are more and more realizing the importance of climate change. And so I think that this is the right time to start change of behavior, because this is what will, to me, will be the key thing, is the change of behaviors for the future in consumption.
Thank you. And ultimately, Camille.
Yes, for me, like an opportunity is like the retrofit opportunities that have savings without like high upfront cost, and it can be like on the midterm interesting before replacing legacy systems, and it's especially interesting for commercial stakeholders. But I think like a challenge is having a clear roadmap on what to do, what technologies would be interesting to have, and I think that maybe commercial actors have a lack of visibility on the solutions and the like on the horizon at when they should implement these like opportunities. And I think it would be crucial in the next few years to really to promote the uptake of decarbonization.
Thanks. And finally, Guilherme.
Yeah, so I think considering the commercial sector, the biggest barrier is their awareness and understanding and engaging with these technologies, but also that there is a big opportunity right now, especially for this small and medium business. Are the smart meters that are getting, so they can engage and have better energy management actions with these technologies.
Great. Sorry for going a little bit over time, but I think it was a fantastic discussion. Thank you all for all your inputs, and again, great job on your presentations and hard work. Thank you.
Thank you.
Yes, thank you, Group 1, for your presentations, and also to Piotr for leading such an interesting discussion. We're now going to move into our second session, which is on supporting the grid through smart and flexible energy networks.
Good afternoon. I hope everyone is well. My name is Michael Azi, and on behalf of my team, we are very excited to speak to you today about supporting the grid. If we want to achieve net zero by 2050, we need to become friends with uncertainty. Uncertainty is the gap between what we know now and what we don't know yet. Will there be a random failure in the gas plants tomorrow? How many people will charge their electric vehicles at this time next year? Will it be sunny next week? Probably not in the UK, but who knows? Amidst these questions, one reaction is to throw our hands up in the air and just plan in light of the things that we have experience with. In the context of the power system of the future, this head in the sand approach will result in very inefficient spending for very little benefit. Another approach is to face uncertainty forthrightly and use it to our advantage. This team explored how we can partner with uncertainty in supporting the power grid of the future, and this is what we'll present to you today. In order of appearance, we'll have Maria Jose, who will take us through how to accommodate uncertainty in the tasks of maintaining a power system's stability. Next, Owen will demonstrate how the next generation of energy technologies can capitalize on uncertainty whilst supporting the integration of renewables. Then I will look at the future power system of South Africa and what benefit there could be in creating flexible nuclear systems. Guillermina then looks at how Uruguay can deploy an EV charging infrastructure, considering the uncertainties from future demand and technological improvements. Camille will then take us through how flexibility can be maximized in smart districts, given the difficulty of having accurate demand forecasts. And lastly, Nadia will look at the system performance of compressed air energy storage systems. Now that you've met the team, I'll leave you in the capable hands of Maria Jose.
Thank you, Mike. Good afternoon to all of you. As Mike introduced before, my name is Maria Jose, and I'll be presenting today the first project for supporting the grid under uncertainty, and it is about the electrical load disconnection allocation in highly renewable power systems. So first, I'm going to start setting some context. In highly renewable power systems, these are characterized by a high penetration of difficult to predict generation that can be centralized, so installed as the power station in the diagram, or distributed, which means it's installed in distribution feeders. This type of generation brings uncertainty into the grids. The issue with this is that successfully operating the system depends on how well its state is known, which translates to how well uncertainty is managed. In this project, we investigated a specific part of the operation of the power systems, which is keeping its frequency stability. If generators suddenly disconnect, there's immediately an unbalance between the amount of electricity being consumed, which is called load, and the generation. This is bad because it makes frequency go to low values that could trigger more disconnections. This happens especially fast in highly renewable systems where its inertia is very weak. The last resource to regain balance is to shed some of the load in the system and avoid a total system blackout. However, for highly renewable power systems, the problem is how to best allocate the disconnection among all the electrical distribution feeders. The allocation is difficult because the feeders with high penetration of renewable resources have uncertain net load, which make their forecast very prone to errors. In the project, we modeled the forecast of the net load of feeders as stochastic variables, using a distribution of values with different probabilities. So these can have different forms, for example, Gaussian, Laplace, Gumbel, and student T distributions. In the figure, we see an example of a comparison between the Gaussian and the Gumbel one. Since the net load of feeders is stochastic, it is difficult to choose where to allocate the load and be sure that the allocation will amount for as much disconnection as required without being overly conservative by disconnecting a lot more load than needed. To address this, we proposed the use of chance constraint optimization, which uses the stochastic modeling of the net load forecast to allocate the disconnection and assure the required load shedding with a certain reliability percentage, for example, 98 or 99%. This makes the disconnection of less load than needed highly unlikely. To make the optimization problem more easily computable, the chance constraint optimization was mathematically reformulated using two approaches. First, assuming that the probability distribution function is always Gaussian, and second, assuming that the shape of the distribution is unknown. Therefore, a distributionally robust reformulation was done. For the Gaussian assumption reformulation, it was found that although the concerns about overshedding are addressed, it is a limited approximation. The reliability requirements are likely not to be met if the probability distribution is not Gaussian, especially for heavily tailed distributions, which could represent more probable extreme scenarios, as, for example, very sunny or very windy days. On the other hand, the distributionally robust reformulation can provide a mathematical guarantee for distribution system operators for the reliability requirements being met. However, the expected load to be shed is highly probable to be greater than needed to keep the necessary reliability, as compared to the Gaussian reformulation in this diagram. This leads to over-conservatism and translates to greater operational costs. To conclude, then the chance constraint optimization formulations can help the distribution system operators to guarantee an optimal allocation of the load with a certain degree of probability. Nonetheless, further work must be done on the relationship between robustness and conservatism of disconnection. Now, Owen will continue.
Hello. Hi, everyone. My name is Owen O'Connor, and I'll be discussing my project, which focused on machine learning for electricity price forecasting and energy storage applications. So, as Maria Jose already touched on, the very nature of renewable energy sources like wind and solar creates more uncertainty in the supply of electricity. In the British wholesale electricity markets, we can already see the effects of this. The half-hourly imbalance price, which is usually below £150 per megawatt hour, has continued to surpass record highs, reaching upwards of £4,000 per megawatt hour several times this year already. What if the next generation of energy storage technologies, like batteries, capitalized on this uncertainty? Storage asset owners can buy electricity when the price is low and sell when they think the price will be higher. More accurate forecasting leads to superior trading performance, which increases profit. Ultimately, profit is what drives investment, which in turn unlocks more opportunity for the next generation of energy storage technologies. Our system will be better equipped to deal with the uncertainties related to renewable energy with an array of thriving storage technologies in support. So throughout the market, participants are increasingly generating forecasts with machine learning models to inform their decision making. This is because machine learning models can effectively capture complex non-linear relationships between market price indicators and the price itself. In this project, 5 different machine learning models were constructed, optimized, and trained using real market data to forecast the half-hourly system imbalance price. The abbreviations of these 5 models are shown in the middle of the slide here. The first aim was to understand how these predictive accuracies of the models changed over a 12-month evaluation period. After this, could individual forecasts be combined to enhance the strengths and mitigate the weaknesses of individual models? So after evaluation, all 5 models possessed reasonable predictive accuracies, each outperforming several benchmark methods. Despite this, the predictive behaviors of individual models were diverse. For example, the RFR forecasts captured the general price movements, whereas the LSTM's more volatile forecasts responded better to fast price fluctuations. Another interesting feature from the results was that predictive accuracies did not correlate with model complexity. The RFR was one of the most accurate individual models, but arguably the simplest in terms of structure. There was no evidence that any of the individual models was significantly more accurate than every other model over the entire evaluation period. This validated the second project aim, which was to explore several ensembling methods. So one of the methods developed in this project was coined expert selection. In this ensemble, model forecasts are stored in a gate and their errors calculated. The gate then assigns weights to each of the individual forecasts based on performance from the previous 24 hours. So it's been established that individual model accuracy changes through time and under different market conditions. This animation shows the weights constantly adapting to reward models that are performing well and punish those that aren't. After evaluation, the forecasts from this ensemble outperformed every other model and method to a level of statistical significance. So what's the impact of this? Using a diverse range of forecasting models with an effective ensembling approach is computationally inexpensive. This is valuable to smaller market participants, such as new storage asset owners who may be financially restricted. This opens an opportunity to prosper through uncertainty. Diversity helps to drive innovation. Comparable to the individual models in this project, a range of energy storage technologies will play a role in enhancing the strengths whilst mitigating the weaknesses of a sustainable power system.
From Owen's deep dive on machine learning and price forecasting, we zoom into a specific power system as we turn our focus to South Africa. In this section, we looked at flexible power generation through thermal energy storage integration. And just to remind you, my name is Michael. So South Africa's power system is very coal dominant. This is likely going to change in the upcoming years in light of a planned 400% increase in renewable capacity by 2030. Now, this sounds great, but this may introduce some instability into the already unreliable South African grid. One way to address this increase is by increasing the flexibility of the grid, which addresses the uncertainty of having too much renewable energy when the sun shines or when the wind blows, and having too little energy when these resources are unavailable. Energy storage is one of the best ways to introduce flexibility, particularly through utility scale battery storage. The only issue with regards to the South African context is that it is really expensive. However, thermal energy storage is a significantly cheaper option, but it needs to be paired with a good thermal source. Therefore, in this project, we explored the benefit of retrofitting the existing 2 gigawatt nuclear power station in South Africa with thermal energy storage to make it flexible. To do this, we formulated an optimization problem for a future 2030 and 2040 power system. And what we did is we described the future electricity demand as well as the generation technology power mix. And then the model would then optimize the number of units in operation of each technology and their respective electricity output, such that the overall annual operating cost is minimized. With this optimization model, we also performed 15 studies with respect to each future power system. And these studies took the general shape of modeling a baseline power system for the years 2030 and 2040, and then swapping out the conventional nuclear units with either of 2 configurations of flexible nuclear units, so either the PPC or SPC. I can speak more about those during the panel discussion if you're interested. We also developed other scenarios that addressed and investigated the effect of introducing utility scale battery storage and increasing the carbon price. Now, looking at the left plot, what we found is that when any of the flexible nuclear options are implemented, there are savings of at least $25 million annually. What was also interesting is that an additional 2 gigawatts of grid battery scale, or of utility scale battery storage in 2030 relative to the baseline is much less beneficial than introducing flexible nuclear units. But this does change going into a 2040 power system with significantly more renewable energy. The plot on the right shows a power generation profile in a 2040 power system, where you can see solar is represented by yellow, wind by blue, and then the demand is represented by the pink line. What we can see is just how much excess renewable output there is relative to the demand at certain points, thus justifying the benefit from having grid-connected storage technologies like battery. But after the costs of implementing the different flexibility measures are included, it was found that only the PPC flexible nuclear units resulted in a lower, or rather in a relative benefit greater than 1. And what this means is that for every $1 spent on implementing the measure, we got almost $2 in savings over the lifetime of the assets. So what we also found was that at the moment, battery storage may just be too expensive for South Africa with such a low relative benefit and long payback time. So how can uncertainty become our friend in this case? Well, it seems South Africa does have big hopes of reforming its power sector. But if the country wants to do so optimally, retrofitting the existing nuclear power plants with thermal energy storage systems seems to be a way in which some of the uncertainty of a variable renewable energy supply can be addressed. And now Guillermina will take us through her work.
Thank you, Mike. Hello, everyone. I am Guillermina, and I will talk about adding flexibility while designing an infrastructure system. Traditional methods for designing those kind of projects are based on an expected future scenario. They are highly risky since it is impossible to have accurate forecast of cash flows for the whole project duration. Flexibility in design is a promising way to deal with the uncertainties surrounding a project. The literature shows that one way for adding flexibility is through a real option approach. Real options is the right but not the obligation to carry a specific task in response to the new information that become available. My dissertation followed 5 main stages. Design for flexibility must start from an existing design configuration that is referred here as baseline design concept or phase 1. It is observed in practice that designs are often optimized based on a set of deterministic forecasts. The procedures in phase 2 help designers identify and model major uncertainty sources affecting life cycle performance. Under phase 3, designers generate concepts to deal proactively with changing operating conditions identified in the previous phase. Each concept is comprised of 1, a strategy, and 2, enablers in design and management. The outcome is a set of flexible concepts that can deal better with uncertainty than baseline concepts. In phase 4, designers explore the system space for the most valuable system design and decision rules to operate the system. Finally, in phase 5, proposes procedures to set favorable conditions for flexibility generation. Phase 1, as it was explained, consists of building a baseline model based on standard design techniques. This baseline model is the current state of the EV infrastructure and its planning expansion. The upper part on the left shows a general bus diffusion model. This model depends on 3 parameters: the coefficient of innovation, which is the external influence or advertising effect, the coefficient of imitation, which is the internal influence or word of mouth effect, and the size of the market. The graphs on the upper right represent the modeling of demand as deterministic. Cost of technology was modeled using a learning by doing curve, as it can be seen in the bottom. Using what I explained, I found the minimum number of charges needed to supply the market based on peak demand. One way of dealing with uncertainty is by allowing the system to change as future conditions unfold. After studying the system carefully, there are 2 primary sources of uncertainty to consider: electricity demand and technological improvements. Electricity demand was modeled using a bus diffusion model and technology cost with a learning by doing curve. Uncertainties were modeled by varying the parameters of each distribution across 2,000 scenarios. Each source of uncertainty can be tackled with a different decision rule. The decision rule that will tackle the demand uncertainty is the expansion, and the decision rule that will tackle the technology uncertainty is the switching technology option. Each decision rule will reduce the risk associated to unfavorable scenario and take advantage in a favorable scenario. The benchmark design is used to compare alternative arrangements. All of them were evaluated under stochastic simulation of the uncertainties with a Monte Carlo simulation. Both designs improve the value of the project. Comparisons between the benchmark and flexible design can be observed in the box plot. It is noticeable that the expected NPV is higher in both flexible designs, which implies that the value of the project has been increased. In addition, the minimum value of the NPV has also been increased. Hence, the risk is reduced. The same conclusions can be derived when analyzing the cumulative distribution functions on the right. The flow of average is the principle that states that the average value of the project is different from the value of the performance under average conditions, which is reflected here. To conclude, the purpose of my work was to quantify the value of flexibility as the difference between the value of the flexible design minus the value of the inflexible design under stochastic conditions. My main message today is that flexibility in design changed the focus from optimizing the design based on a set of deterministic forecasts to optimizing this design for effectively performing for all the possible outcomes. Now, Camille will follow.
Thanks, Guille. Good afternoon, everyone. My name is Camille, and I'm going to introduce you my work on flexibility within smart districts. Like all the other members of this group, my work considers uncertainty to be an inherent element of the energy transition. However, as Guillermina had just before me, the core of my work isn't to try to reduce this uncertainty, but rather to see what impact it could have on the performance of a smart district. So to reuse Michael's words, I try to see how, from a district perspective, we could become better friends with uncertainty, and what would be the cost of such a friendship. So first, a bit of context. What is called a smart district is a district in which each building can either produce electricity, thanks to the solar panels they have on their roof, or consume electricity. And this consumption of electricity can be done either directly from the grid or by discharging the central battery. Therefore, there are 2 sources of uncertainty in the forecasts: demand and PV production. Now, how can a bad forecast affect the energy performance of a smart district? To answer this question, we must understand how the central energy system of the district works. So every day, forecasts of both demand and PV production are generated for the next 24 hours. Using these, the use of the central battery is optimized in order to minimize the daily cost of operation. The outputs of this optimization are instructions that are given to the battery, telling it when to charge and when to discharge during the next 24 hours. But obviously, the actual demand and the actual PV generation are never exactly the one we forecasted. Therefore, the instructions given to the battery are not perfectly adapted to the situation. But still, the district energy system must match demand and supply. So with the wrong battery instructions, this can result in extra costs. So to make all this a bit clearer, let's take a quick example. Here at around 5 p.m., we can see that demand has been underestimated. The cost is at its maximum, so we shouldn't be buying to supply the district. Instead, we should use the energy stored in the battery. However, the instructions given to the battery at 5 p.m. will be, according to this dashed line, to discharge the battery, but not enough to meet the actual demand. Therefore, to satisfy the demand, we will have to buy energy from the grid when its price is at its maximum. If the demand had been perfectly forecasted, we could have avoided these extra costs. So this model enabled me to use the difference of cost at the end of the day between the studied scenario and the theoretical one, which is a scenario in which the forecasts are perfect. And this difference of costs was my indicator for performance. I then looked at how this indicator was affected by different factors, such as the quality of forecast, the season in which we work, and so on. But the factor on which I focused the most was scale. My question was, are there any benefits to working at a district level rather than at an individual building level? And the answer is yes. Indeed, the uncertainty in the demand forecast comes from the difficulty to predict individual occupant behaviors, such as, for example, when they will charge their electric cars or fill a hot water bath. Therefore, if you consider many buildings, in the end, they will average up, and the demand forecasts will become better and better, and so will the operational cost of the district, as it can be seen on the graph. To conclude, too often, uncertainty is not considered enough in the studies where the energy flows of a district are modeled. The purpose of my work was to quantify this error and to show how to lessen the impact of uncertainty, which led to the recommendation of managing energy at a district scale. Now, over to Nadia.
Thanks, Camille. Hi, everyone. I'm Nadia, and I'll be presenting on improving the efficiency of compressed air energy storage, shortly referred to as CAS. As shown by the three previous presenters, energy storage serves as a buffer and prevents the curtailment of expensive energy resources. But beyond batteries, thermal energy storages, and the old-aged pumped hydro, there exists CAS, a proven technology already in operation for several decades in Germany and the US. It bears numerous benefits such as high energy density, long discharge cycles, high durability, and is less geologically constrained compared to pumped hydro. Additionally, there exists the potential to use existing salt caverns or natural rock formations as air storages. Overall, CAS has a low cycle cost. However, it is limited by its system efficiency. Therefore, for this technology to effectively compete against batteries and pumped hydro, especially in locations where the geology and the application supports its use, high performance systems operating at low cost are imperative. Over the years, there has been several CAS concepts presented, but this study focuses on adiabatic CAS, which generally consists of a compression train, thermal energy storages, air storage vessel, and an expansion train. However, to propose high performance systems, it is important to understand which of these components within CAS affects its performance the most. Therefore, I focused on varying parameters such as the operating mode of the system, the size of the air storage vessel, the operating pressure, and the pressure ratio of compressors and turbines. Based on the operating mode, I considered 4 system layouts, employing either a constant volume or constant pressure air storage. The difference in the first 3 designs shown here is in the number of throttle valves used, 1, 2, or none. As a background, throttle valves allow for constant pressure operation of the compressors and the turbines, which currently have fixed pressure ratios and therefore unable to produce the varying pressures required by a constant volume storage. So I developed thermodynamic models of these different layouts using data from open source literature. And the model build simulates the charging and discharging process for the different parameters that were tested. And at each time, we calculated the thermophysical properties of air, the efficiency of the system, the work potential stored in the TES versus the ASV, and more. The results show that the more throttle valves the system had, the less efficient it was, as throttling results in a non-negligible loss of useful work potential. The constant pressure system was more efficient for all the tests that were conducted, but not significantly more than the non-throttled isochoric system. This suggests that the ability of compressors to operate at varying pressure is important. The size of the ASV and the operating pressure affected the performance as well. Low efficiencies were observed with decreased values of both parameters. The pressure ratio also affected the efficiency of the system, as is shown in the graph, but most importantly, it had a higher impact on the outlet temperature of the air after expansion. We observed that wrongly pairing the pressure ratio of compressors and turbines resulted in either too cold or too hot an outlet. Both outcomes are not ideal in terms of energy economics and the environment. And finally, based on the exergy calculations, the study reconfirmed that integrating CAS with TES is essential, as more work potential is stored in the form of heat. So thank you for listening. I'll hand over to Michael.
Thank you, Nadia. So to summarize, Maria Jose took us through how to accommodate uncertainty in the tasks that maintain the power system's frequency stability. Then Owen demonstrated how the next generation of energy storage technologies could capitalize on uncertainty whilst supporting the integration of renewables. My research then concluded that integrating thermal energy storage for flexible power generation allows power systems to save money in a system with increasing uncertainty from rising levels of renewable energy. Guillermina then stressed the importance of including flexibility from the design stage in a long-term project with high capital costs. Camille then explained that at a district level, neglecting uncertainty in demand results in significant additional costs, and these could be avoided by using better quality forecasts or by considering a large number of buildings within districts to get rid of that uncertainty. Then lastly, Nadia just showed us that the operating mode of an adiabatic compressed air energy storage system is key to achieving high performance systems. So what we've seen today is that incorporating uncertainty into the way we conceptualize future energy systems is essential to the energy transition. We believe that this is true across multiple levels of consideration. It's particularly exciting to consider the huge progress in the space of AI and machine learning techniques, especially in light of the increases in computing power. The question then becomes for us about what effect these new ways of incorporating uncertainty will have on market regulation, technology adoption, and future business models. And these questions can only be addressed if we do indeed become friends with uncertainty. So thank you for listening, and we look forward to the panel discussion later.
Thank you, Group 2, for your presentations. It was really interesting to see such a wide range of ways at looking at flexibility. For our discussion, I would like to introduce Ajai Ahluwalia, who is Principal Strategy and Business Developer at Equinor, who will lead our discussion now.
Good afternoon, everyone. Well, firstly, I'd just like to say thank you for the opportunity to witness such interesting presentations and such interesting content. I completely acknowledge the point around uncertainty. So my first sort of opening question I'd like to sort of discuss with the group is, you talk about uncertainty as if we're already dealing with a system where we are subject to those changing factors. To what extent has in each of your projects have you thought about incentivizing the consumer or incentivizing demand, and how would that factor into the various pieces of work that you've all looked at? And to the audience, I would just say, We are looking at the Q&A section, so please drop in your questions, and I'll do my best to bring those and raise those points as well. And maybe if I start with Nadia first, if that's okay.
Sure. So because my dissertation, my project mostly focused on improving the efficiency of an existing system, I did not look at anything from the consumer's end in terms of like demand. So I think I would pass it on to Maria or Owen. And also Camille. I think they're in a better position for that.
Okay, Nadia, that's a fair point, but I do have some questions for you coming up, so you're not off the hook. So I think Nadia nominated Maria. Maria, do you want to jump in?
Yeah, hi. Well, so my project really looked at the uncertainty in the demand and the net load of distribution feeders. So in this case, we did acknowledge that that uncertainty actually comes from the fact that, well, first, we don't have a perfect forecast and a perfect knowledge of how much distributed generation there is. And of course, there's also a side of uncertainty coming from the demand behavior, right, in those feeders. So from this first stage of the project, we just assume that these feeders have this uncertain net load, and that getting or improving ways in which we can observe the power system better, for example, and having, of course, better forecasts would help in such schemes, for example, under frequency load shedding schemes, which was what we looked into. But we didn't look specifically into disconnecting in such a distributed way, for example, meter by meter in each of the consumers. So that wasn't specifically the focus of my research, but it does have an impact, right, on even the high level, which is the whole distribution feeder as we looked into. So I don't know, maybe I think Camille would have some thoughts on it, and Owen maybe too.
Before we move on to Camille and Owen, can I just ask one small question? Did you, as part of your distribution analysis, was it based on, did you say that you modeled data? Is it based on a real system, or was there a general model for a generalistic model? Was it, did you use real data to understand how a distribution network was operating?
Yeah, so right now the focus was really to develop the methodology and to have a method that is ready to accommodate all kind of data that you can have, right, from the power system. So to demonstrate the use of the methodology, we artificially generated a case study, a very basic case study with, a limited amount of feeders, and just assuming that in this case we had data that we analyzed and that we could know what the, for example, expected value of that net load was, and the standard deviation of that forecast could be. So the method is actually ready to accommodate a set of data that can be characterized by those first two characteristics of the statistical distribution, let's say, of those measurements. But we didn't use real data in the project. Yeah.
Okay, thanks, Maria. Camille, over to you if you're okay to jump in at this point.
Yeah, sure. So to answer the question about the different inhabitants' behavior and how it can impact my work. So I think, as Maria before me, it was really the core of my work to see how we could change the consumer behavior. For this project, I used a model that was already existent, that modeled at a very small granularity the behavior of the different inhabitants of the district I was studying. But I took this for granted without trying to work on different scenarios in which they would act differently to see how it would impact the forecasts. So yeah.
So just as a small example, in your district model, did it assume things such as vehicle to grid charging or smart charging, where people would be charging their cars in the middle of the night as opposed to when they return from work and immediately plug their car back in, assuming non-COVID conditions, of course? But what sort of like baseline assumptions were there in and around that model?
So for the example of the EVs, of the electric vehicles, we consider that, for example, on a 20 building district, we consider that all of them would have charging infrastructure inside there for each building for the electric vehicles. And so we consider that the frequency at which these electric vehicles would be charged was something stochastic, with a frequency that was depending on the time of the day, which means that depending on the different type of EV user, for example, if it's someone that is working during the day, we know that from, let's say, 9 a.m. to, I don't know, 6 p.m., we wouldn't have any charging. But then after 6 p.m., the frequency at which the user would charge the EV would follow Bernoulli law, so it would be something stochastic. And it depends on the type of user for the EV. But in this thesis, for example, there are also some simplifications that had been made. For example, vehicle to grid charging was not something that was studied. And yeah, I don't know.
Okay, thank you. Owen, over to you, sir.
Yeah, I don't have much to add on to it. Camille covered it pretty well, Camille and Maria. But what I will say is that more broadly from my presentation on point forecasts, I think that with schemes like vehicle to grid and small scale batteries in homes, like looking in those scenarios for the future, there will be opportunities for these types of technologies to participate within the electricity wholesale markets to some extent. And I guess that does create a level of uncertainty that we haven't seen yet. But I think that if we are planning for these technologies to be introduced, then I guess it will be fine. I don't really have much to add. Sorry, I was a bit rambling. Yeah.
That's okay. I mean, what I will just do now is I see a question coming in from Teng. The question to you is just he wondered, for the electricity price forecasting, how often would the models, or how often should the models actually be updated? He cites they cite the soaring carbon price and how that would affect the electricity pricing forecasting. Is there anything you can elaborate on, please?
Yeah, that's a good question, because when it comes to machine learning and price in general, supervised learning, which is when you have a training data set and a testing data set, usually in the case of forecasting, that would look something like maybe you would train on historical data for the previous year and then forecast for the next 2 or 3 months. And in reality, that's not how market participants work. They're constantly updating. So with my models, I had to retrain or update the models every half an hour. Well, it was a simulation of every half an hour. So at every price point, it would have to retrain with the most recently available data. It was kind of challenging to organize the data in a way which would allow for this, I guess, forecasting structure. But yeah, basically, the models were retrained at with every latest available point.
And did you train it on a real system like the UK trading system, for example?
Yeah.
So would it have, given the interesting the events of this week with the interconnector coming down, would it have been able to anticipate that sort of event and the associated price spikes?
So yeah, it's a good question, and I think that this year in particular has been a very volatile year, and we're only now starting to collect data. And the way that supervised training works is it's learning from historical data in one way or another. And at the start of the year, for example, we'd never seen prices rise to £4,000 per megawatt hour. So there's no way that a model could predict it was going to be £4,000 per hour. But I think, and this kind of leaks into some other questions that were published, but I think what it could have anticipated was the movement of the market. And I think that can be more important than an actual point price.
Okay, thank you. I'll move on to Michael, and appreciate that the question around uncertainty is perhaps not as applicable, but I've got a question here from Maria, which is, what is the typical scale of an average PPC system compared to the average traditional nuclear plant in South Africa? And did your research include a cost-benefit analysis for the rollouts of such retrofits at scale in order to achieve the mentioned savings? Is that something you can expand on, please?
Yeah, absolutely. Thank you for the question, Maria. So let me first explain what a PPC system is. And basically, well, what it stands for is primary power cycle. And what it is you have your thermal energy storage that the steam from the nuclear energy transfers its energy to the thermal energy storage, which then discharges at times of, low renewable energy output, for example. It discharges that thermal energy into the main power cycle. So so it's an integrated form of thermal energy storage. So the question was, so what's the typical scale of such a system? This is dependent on the thermal energy storage method that you use, in which in my research we modeled a sensible molten salt storage system, which is typically used in concentrated solar power plants. And from my research, I see that the scales of these type of systems range from around about 100 kilowatts to around about 300 megawatts. In my research, I actually modeled this as 410 megawatts for the nuclear system in South Africa. And I did this just because I wanted to show a proof of concept and just kind of model the trajectory of where the technology is going, because the scales of operation of these systems are getting bigger year by year. So in South Africa, what I modeled was a 410 thermal energy storage capacity. And then your next question was around cost benefit analysis. So yes, I did do a cost benefit analysis. And so what my model gave as a result was the annual system operating cost savings. So that's per year. And what I did is I annualized the cost of implementing such a thermal energy storage system for the South African context. And I did this because South Africa is actually looking to extend the lifetime of the nuclear plants by around about 20 years in the next 5 years. So I was thinking, as a hypothetical, what if as part of that extension, we include a retrofit of thermal energy storage in that system? So I included the hypothetical or assumed, I made various cost assumptions about that and measured the cost benefit of that and got a relative benefit for implementing such a system.
Sounds good, Michael. I'll just put this out there. I'm a big fan of us applying all this theory to real life situations and real life problems that we can actually fix. So nice to know that. Just out of interest, you talk about instantaneous power in terms of megawatts, but obviously you've been looking at storage here. So what sort of duration of storage have you been considering?
That's a good question. Yes. So I didn't have much time to go through this in my presentation. So what I did I modeled around about 30 scenarios, and in those scenarios were different storage durations of the different configurations. What I did is I modeled a half-an-hour thermal energy storage and a 4-hour thermal energy storage, just to get like extremes of what I can do with that and what benefit that would be. And what I found was that only thermal energy storage durations between half an hour to 2 hours actually resulted in a benefit for the system. So that's what I did. Yeah.
Okay. Thank you.
Sure.
For my next question, I apologize. Please, if I pronounce your name incorrectly, can you correct me? So is it Wilhelmina? Hi. Sorry.
Yeah, don't worry. It's Guillermina. That's okay.
Okay. We have a question for you relating to the impact on carbon outcomes, not only economic parameters. That's a question from Muslan. I don't know if you can see that, but is that something you can expand upon?
Actually, that was one of my recommendations. I didn't have time to look at the carbon emissions. Of course, I focus on maximizing the NPV of the flexible designs. I am sure if I use another objective function such as reducing emissions, maybe I will come up with another flexible strategy and flexible design. But what I can say for now is that in Uruguay we have 98% of the generation from renewable sources. So I don't think that the carbon emissions are more during the operation of the vehicles, but we will have to assess the carbon emissions during the production and the disposal of those cars. I think those are the most relevant.
Wow, I didn't realize that. So 98% of Uruguay's power is coming from renewable sources.
Yeah, the biggest share is from hydropower. But we have a lot of wind as well.
Oh, that's good to know. I mean, out of interest, I posed the original question here about the incentivizing of people to, in the example of electric vehicles, is incentivize them to charge their vehicles at a specific time. Has that come out as part of your analysis, as part of your thesis?
Sorry, could you repeat the question? I couldn't hear you very well.
Is there some aspect around human behavior when people are, smart charging, vehicle to grid charging? Is that something that came about as part of your analysis?
Yeah, so I didn't find studies in Uruguay, of course. There aren't any studies about customer behavior. So I took studies from the US, from the state of California, and tried to adapt to Uruguayan reality. Of course, future studies in Uruguay should take into account customer behavior. And I also try I tested many new technology. I consider the cost, but I also consider the utilization factor. And I think that smart charging can be related with the utilization factor of the infrastructure.
Okay, thank you very much. Going back full circle, I'm going to come back to Nadia because we didn't interrogate Nadia sufficiently, in my opinion. But coming back to you, got a question from Anonymous here, and then I'm going to jump in as well because they're a big fan of storage at the moment. So the question is, can you elaborate on why compressed energy storage would be able to compete with conventional technologies of battery storage, lithium ion as an example, in terms of in terms of utilities and power production? Can you give us some figures on sort of round trip efficiency, pros and cons, I guess, associated with compressed air versus conventional batteries? And one follow-up question from me specifically, because this is whenever I ask people about energy storage, you've used the term long, I think, at one point. Can you tell us what your definition of long storage is?
Sorry, can you just repeat the last bit?
What is long storage to you, or large storage?
Oh, large storage. Okay. So just to start off with, your last question is the fact that large storage is basically above 100 megawatts. So currently, compressed air storage has similar storage capacities like pumped hydro. So it's above 100 to 300 megawatts. It has that ability, and even beyond that. And I think that to the questions about comparing it with batteries is the fact that because it has that high storage capacity, it has high energy density, its size compared to batteries for similar storage is smaller. So the physical size as to the land space you will need. If you want to store energy in batteries currently, you need a lot of land space for that particular capacity. The capacity we're talking about from 100 to 300. Wherein with compressed air, if you have an underground storage system, by the way, you can have either underground, above ground, or underwater storage facilities. So it makes compressed air very versatile in that sense. So if you have an underground storage system, you're using less space. And compared to pumped hydro again, it is less geologically constrained. So you can actually have compressed air in locations where renewables thrive better, unlike pumped hydro. In the case of batteries, because pumped hydro has the capacity to use underground storage, and those underground storage are they're naturally occurring. It could be hard rock, it could be aquifers, it could be salt caverns that are already there. It reduces the capital cost. There's a paper by Pim that I included in my research that estimated 0.09 pounds per kilowatt hour in 2020 money. So obviously with inflation and everything, that amount is completely different right now, but 0.09 pounds per kilowatt hour using underground storage. So that is really, really low. But as I mentioned, it is currently hindered by its system efficiency. So at the moment, it's between, well, studies for adiabatic are between 50 to 70. The highest that has been achieved is 68% from the papers that I read. And in my studies, in my study that I conducted, my highest efficiency was actually 63%. This is not competitive when you compare it to batteries that have super high efficiencies in the 90s. But when we talk about scale, there are some benefits. And I want to just mention that there's no one-size-fits-all storage system, and that there are instances where obviously battery is perfect for it. But in situations where the geology and the application supports for cast uptake, it is very important that these technologies are in a position to be able to thrive. So I think I've covered the round trip efficiency, the CapEx, and just for the footprint, I should mention that currently batteries are, what should I say? So the end of life for batteries is a very controversial topic at the moment because there's no solution for what is going to happen to all those batteries once we're done with them. And they have a short duration. So they're from 10 to 15 years, if I'm correct, their lifespan. So after 15 years, we have to start thinking, what are we going to do with those batteries? And there's no recycling, well, a solid proof recycling solution for it. Where in the case of CAS, the two technologies that have been commercialized have been running for over 4 decades now. So their durability is longer, and it's just metals, it's just compressors and turbines that we have to worry about their end of life, and we know how to handle those. So yeah, that's it.
So very quickly, Nadia, because it is my soapbox item. So you mentioned instantaneous power, but the capacity of a compressed air storage, how many gigawatt hours are we talking? Are we talking megawatt hours?
I can get back to you on that figure.
No problem. Okay, well look, I've got Connor on the chat telling me that we've only got a minute left. So I mean, look, I just want to say something, which is that, thank you to Imperial for inviting me back. I want to say a huge well done to the students here who've done some really interesting and thought-provoking work, and over what has undoubtedly been a very challenging year for all of us. So to see you deliver such interesting and relevant work is a real pleasure. Looking at the work, as someone who is an engineer at heart, I would just say, look, it's always interesting when you are thinking about these different topics and understanding what the problems in various systems you are trying to solve, and relating that always back to the need. And I think with such great minds developing these ideas, I'm confident that we are going to meet our sort of various national targets with regards to decarbonisation. So pleasure to listen from you today, and I'll pass over to the next panel. Thank you very much.
Thank you, Ajai, for chairing the panel session, and thank you, team, for answering all the questions really well. So we should just move on to now session 3, which is energy for development and meeting the Sustainable Development Goals. Thank you.
Welcome everyone to the presentation of group number 6.
Our common theme is energy for development, although we summarize the contents of our presentation as follows. Benefits of transitioning to sustainability across world regions. Before moving on to a brief introduction to our common theme, let's quickly glance at our speakers today. Livio will kick us off with Ani, Blanca, Arthur, Daniel, Imran, Sebastian, and Fatima following, before Daniel will wrap things up with a brief conclusion. The term development is used fairly loosely to situate our research, and therefore we would like to define it. In this presentation, by development, we mean the achievement of the Sustainable Development Goals, or SDGs. The 17 goals are a blueprint to achieve a better and more sustainable future for all, and were established in 2015 by the UN General Assembly. They are supposed to be achieved by 2030. Our group focuses on 6 of these SDGs, which you can see highlighted on the left. It is important to emphasize that we view the term development holistically, that is, as something that all countries need to do better to achieve sustainability and other positive socioeconomic outcomes. The 6 SDGs discussed can broadly be grouped into 3 areas: health and water, energy, and cities. You will see the specific goals each presenter is discussing mentioned in the upper right-hand corner of their slides. Furthermore, the geographic focus of our presentations lies on Burkina Faso, Nigeria, and South Africa on the African continent, as well as the United Kingdom. So without further ado, the floor is yours, Livio.
Thank you, Sebastian, for introducing the UN's vision. My dissertation focused on modeling the health co-benefits of climate change mitigation in urban centers and aimed to advance SDG 3, good health and well-being, and SDG 11, sustainable cities and communities. In essence, this research was designed to assist policymakers in developing holistic policies and was split into 3 separate chapters. First, a systematic review was conducted to support decision makers who must have an extensive understanding of the topic to develop effective policies. Next, stemming from the findings of the review, an all-inclusive and open-source framework that can comprehensively quantify the health co-benefits of traffic reductions in urban settings was offered. Lastly, the framework was applied to 3 hypothetical traffic reduction scenarios to check if using reduced form models for preliminary screening is satisfactory or if more intricate analysis is required. Did you know cities occupy 3% of the world's land but account for 75% of global greenhouse gas emissions? These concentrated impacts are a direct threat to public health, with the WHO estimating that air pollution and physical inactivity are responsible for millions of deaths every year. A potential solution to address these issues lies in adopting a systems thinking approach. This leverages synergies across sectors, generating environmental, health, economic, and social co-benefits, as highlighted by the systematic review discussed in the following slide. Starting from 8,878 articles, 21 fit the eligibility criteria, revealing an abundance of pathways to increase policy effectiveness. In particular, the intertwined nature of transportation and land use was clear, highlighting the potential to combine interventions to optimize results. However, the majority of the literature relied on the use of complex models built to assess 1 or 2 sectors at a time, somewhat contributing to the detachment of the decision-making process from scientific evidence. Therefore, to address these research gaps, an all-inclusive modeling framework for preliminary screenings of urban transport interventions was developed, described, and tested. The framework outlined was designed to assist policymakers in efficiently modeling the holistic impacts of traffic interventions. It is applicable across Europe and can be adapted to other continents to ensure the Sustainable Development Goals are met worldwide. The framework initiates analysis on Sherpa and Sherpa City, modeling policy impacts on NO2 and PM2.5. Next, the WHO AirQ Plus software combines air pollution and local data to calculate the premature deaths prevented. A proportion of traffic is then allocated to sustainable transport modes, and the physical activity co-benefits are modeled using heat. Finally, the indirect effects on road noise levels and green space exposure are converted into mortality by integrating the Utopia methodology. In the last step, the framework applies value of statistical life estimates to highlight how a systems thinking approach can be economically advantageous. To facilitate understanding of the simulation process, a step-by-step user guide was provided, and 3 hypothetical traffic reduction scenarios in London were modeled. For a 20% reduction in traffic, first, primary impacts on NO2, PM2.5, CO2, physical activity, noise, and green space were found. However, traditionally policies have been examined in a narrowly focused way, and this is where the analysis tends to stop. Instead, by applying the framework presented, policymakers can go one step further and explore the associated health and economic co-benefits. For a 20% reduction in traffic, increased physical activity prevented 346 premature deaths, NO2 prevented 90, PM2.5 prevented 18, noise prevented 67, and green space prevented 39. This also generated vast economic savings, as for London, the value of a statistical life was estimated to be worth £2.95 million. These results were in accordance with published literature, revealing that the health co-benefits of modifying travel habits are substantial, cost-effective, and attractive to multiple stakeholders, thus must be considered to gain a proper understanding of policy impacts. Finally, the findings from the systematic review, framework development, and case study were critically evaluated to provide policy recommendations and advance the UN's Sustainable Development Mission. For starters, the research highlighted the need to focus on redesigning cities for active transport, as this is healthier, greener, and cheaper than a carbon-neutral fleet. Moreover, to concentrate impacts on local populations, and as a result of the transboundary nature of PM2.5, policies are better off focusing on controlling NO2 pollution. Lastly, it is vital that the monetary value of co-benefits is considered, as this can help widen the rationale for climate mitigation by highlighting non-environmental impacts that resonate with the public. In conclusion, if the right steps are taken, cities have the opportunities to leverage the climate change battle, promote good health and well-being, and build a foundation for sustainable and resilient urban centers.
Thank you, Livio, for sharing your work. Hi, this is Anyi, and now I'll move on to the number 6 Sustainable Development Goal, clean water and sanitation. I focus on the design and evaluation of rainwater harvesting system, which is used to solve the water shortage issue in commercial buildings within the United Kingdom. By 2050, if there are no actions to reduce water consumption in the UK, there will be a 15% reduction in available water. Also, buildings account for around 40% of emissions and 16% for water usage. Therefore, it is important to make the buildings more sustainable. Many concepts are discussed for this purpose, like the living buildings. Within the living building technology, the net zero water system is useful in solving water scarcity. Rainwater, as a natural resource, is an ideal supplement water source in the net zero water system, such as rainwater harvesting system. The rainwater harvesting system is used to replace maize water with rainwater in applications like toilet flushes. Therefore, I aim to find optimal rainwater harvesting system design for UK commercial buildings. The figure is the system's working principle, and here are 5 main parts: catchment roof area, pipe system, water tanks, filtration system, and water pumps. Among them, I pay particular attention to water tank design, since it changes largely from case to case. In past studies, the system was designed using a simulation model. The optimal design was usually found by only considering the system's technical or economic performance. Therefore, my project aims to find the optimal rainwater harvesting system design based on its performance from 3 sections: technical, economic, and environment. To achieve this goal, the optimal design was selected from a series of design results based on 3 key performance indicators: water saving efficiency, payback period, and operating carbon savings, which represent 3 different sections. Moreover, case studies across the UK have then been applied to validate and test the design methodology. Rainfall is important in the system, so the case study selection is based on the rainfall level, and this is the UK rainfall distribution map. Besides the rainfall, demand and catchment roof area are also important parameters. This table presents the Tedley case study result. It shows that the catchment roof area could significantly change the design and the system's performance. However, the simulation model could only show the carbon saved by not using the mains water through the OCS indicator. The system's environmental impacts have not been investigated. Therefore, the life cycle assessment method is introduced. The study system is a cradle-to-use gate system, and the functional unit is 1 cubic meter of rainwater supplied. There are 4 impact categories: global warming, ozone formation, terrestrial acidification, and water consumption. From the results, the water tank is responsible for most environmental impacts. Hence, the importance of water tank design is highlighted again. Based on the 2 models' results, several parts are recommended to be focused on in the design process. First is the storage fraction, which represents the relation between tank size and the rainfall catchment. It is useful in defining the scope of the optimal tank size. The second one is the catchment roof area, which can change the design and the performance. Location is important since it defines the rainfall level. Moreover, minimizing the tank size and using environmentally friendly material is crucial in reducing the environmental impacts. The policy is also important in raising the use of the rainwater harvesting system. Government support, like subsidies, will make the system more attractive by reducing the payback period. And the rainwater quality policy is required to make sure the system provides safe rainwater. The LCA result shows that water consumption is required when using rainwater. So in the future, if the LCA model can be directly combined with the rainwater harvesting system simulation model, the study would result from a whole life cycle perspective. As for the application of the rainwater harvesting system in other countries, it is theoretically useful. However, considering UK and Africa has different rainfall scenarios, more case studies are required to see if it is still a cost-effective system in Africa. Thank you.
Hello, my name is Blanca, and I'm focusing in SDGs 11 and 12, which refer to sustainable cities and communities and responsible consumption and production. My research is a holistic eco-efficiency preliminary study for designing the bio-waste strategy in Old Oak and Park Royal. The need to decelerate the impact of climate change has never been so pressing. With waste rising proportionally to macro global trends, more advanced management schemes must be implemented. A special emphasis should be made on bio-waste due to its predominance in urban areas and the fact that all the materials have already been successfully integrated into recycling schemes. International pressure encourages to take action, providing significant support to technologies such as anaerobic digestion due to the duality of its energy potential and more frequently require nutrient looping. The case study in Old Oak and Park Royal is selected because the regeneration project that is currently being carried aims to create a reference sustainable community. It also has room for improvement in this subject and is characterized by the significant presence of the food and beverage industry. Bio-waste in this area is collected door to door with diesel trucks and mainly treated by incineration. But is this currently the most economical and sustainable option? The waste problem cannot be tackled from a single perspective, since waste systems encompass waste generation to its final disposal or usage. Consequently, full modeling is required to find the optimal management strategy and commit to current needs. Inspired by the SWOL framework, where diverse inputs are interconnected, I propose a multi-stage parameterized program to test innovative collection systems, decentralized treatment, and valorization routes. Although the late emerging of different energy from waste technologies, incineration and AD were selected due to their maturity, versatility, and scalability. However, given that the AD infrastructure is not currently in place, following recent improvements, its decentralized option is considered for avoiding a transportation stage. With help of 3 softwares, MATLAB, ArcGIS Pro, and CIMA Pro, different inputs were obtained to later assess the repercussion of the maximum revalorization designs. The results showed that segregated collection can bring many benefits, and its implementation is strongly recommended. Electric trucks are also found as the optimal solution for collection and allow a gradual transition or investment. For the treatment and valorization options, results were more dispersed, but the scenario with incineration, BECUS, heat, and fly ash valorization is the most suitable solution for this project. Since the incineration capacity is currently built, the implementation of BECUS dramatically upgrades the use of this treatment, creating the earliest scenario where the system is ecologically and economically positive. The proposed solutions would enhance the Old Oak and Park Royal waste system. The economic benefits brought could be redirected for the improvement of other public services, hence promoting SDG goals 11 and 12 by creating a healthier and sustainable community and increasing resource efficiency. Conversely, the results also recall the importance of developing more cost-efficient AD designs, since although being the most eco-friendly treatment, economically cannot be compared to incineration, especially in urban environments. Given the recognized capacity problem in London, decentralized incineration and heat recycling projects should be explored in the future because of their many benefits. Although being a preliminary study and demanding further works to assess concrete aspects of the project's optimality and feasibility, diverse and insightful trends were extracted to aid decision-making in regeneration projects. Besides, some recommendations were also identified, highlighting the importance of exploring in more detail the electric trucks charging infrastructure and their environmental impact, using previous incineration projects as reference models, boosting Becu's technological readiness, prioritizing reduction of waste generation, possibly with incentives, and the relevance of public satisfaction, which can be increased through surveys and awareness campaigns. Thank you.
Hello, my name is Arthur Pereira, and following the topics explored by Blanca in terms of managing waste in a sustainable city, my topic looks at the impact of aggregating power purchase agreements in an urban industrial area, taking Park Royal as case study. This looks to tackle SDG Goal 8, Sustainable Economic Growth, and 11, Sustainable Cities. The project came from OPDC, the urban developer of Park Royal, when faced with challenges as the idea of solar panel implementation was brought to the businesses of the area. The first two main challenges that they saw were just the high initial capital cost of implementing solar that small businesses just don't have. Furthermore, there was just a general resistance from the businesses as this project was just not seen as priority, especially with last year's impact from COVID. To tackle these, power purchase agreement can actually be useful to use and have been seen in other projects. These allow for a developer to actually own the PV and provide the buyer with the electricity for a fixed price. There exist three types of PPAs. The first one being behind the meter, where the PV is directly on site. Secondly, sleeved, where the PV and the buyer are still physically connected and the grid transports electricity from one to the other. And finally, a virtual or financial PPA, where the PVs and the buyer aren't actually physically connected. The generator sells to the grid, and then the amount transferred between parties is the difference between the wholesale market and the fixed price. Other challenges do, however, exist and aren't really solved by that. The first being just the urban environment, where not all buildings can actually accommodate for solar. This restricts who can actually partake in this and who can benefit from such project. Secondly, smaller projects are seen with a PPA from a developer as uneconomic, are usually not pursued. And finally, there's a long-term commitment needed when it comes to PPA, and this can be seen as too risky for some businesses and just as a main hurdle to tackle. To answer these challenges, a combined behind-the-meter and virtual structure was designed. It looks to capture the benefits from a behind-the-meter PPA by avoiding electricity transport costs, while adding the flexibility of a virtual structure to create and aggregate a support structure for small businesses. So now taking a look at some of the results from the studies with the scenarios where exporting electricity were not permitted, meaning all electricity produced is used by the building, we can get an insight into the value of such a structure can have, as well as the role that different buildings can play in. The main point to understand before looking at the result is that buildings 6, 19, and 20 represents larger buildings in the area, while the rest are similar smaller buildings based on demand. Building 11 and 20 weren't allowed to have solar, and finally, in the UK, smaller consumers pay a higher retail price for the electricity they use. Looking at the left graph, we can see that the solar placement with and without aggregation allows for smaller buildings to see an increase in solar place, leading to an overall increase in capacity of around 20%. Furthermore, looking at the right graph, we can see the contribution of sharing of each buildings. The larger buildings play a main role as energy sink for the excess solar of smaller buildings. Larger buildings with no solar place represent actually 60% of all inflow electricity. It should be noted, though, that the level of sharing was relatively small with only 0.3% seen due to the 2020 wholesale market being much lower than the current PPA prices. Results of the study allow us to make 3 important points. The first being that aggregation allows smaller buildings and buildings that can't put solar on their roof to participate in the project. But to enable such a project to occur, there needs to be building with no solar, as this allows to add resilience to the structure and absorb the excess solar of others. Finally, if more sharing is wanted, then there needs to be a drop in the PPA price to the level of wholesale market, which will make sharing more profitable at greater times.
Thank you, Arthur. And to continue our discussion about how Goal 11 could be achieved, I would now like to focus on the transport aspect of sustainable cities and communities by presenting my project that focused on the analysis of lithium-ion battery pack degradation consequences on the costs of owning a plug-in hybrid electric vehicle in Great Britain. A key part of achieving Goal 11 is ensuring affordable and sustainable transport. In the developed world, and in the UK in particular, the current trends would suggest that battery electric and plug-in hybrid electric vehicles will occupy the largest share of the market in the near future. This can in part be attributed to their reduced tailpipe emissions and the possible operational cost reductions compared to internal combustion engine vehicle powered cars. Nevertheless, electric vehicles are not without their faults. More specifically, these forms of transport rely on lithium-ion battery packs as the means of onboard energy storage, and using such vehicles will cause their battery packs to degrade. Though studying this phenomenon can be time-consuming, modern computational capabilities can significantly simplify the issue, and for my project, I developed a battery pack degradation model combined with an equivalent circuit model in MATLAB and Simulink to study the possible consequences of using a pack comprised of 2 cells connected in parallel under a variety of thermal conditions. After running these models, I found that a key effect of degradation is the reduction in pack charging efficiency, which is caused by the increases in the cell internal resistances. The largest efficiency reduction was noted when both cells of the pack were held at 20 degrees Celsius, while the 45 degrees Celsius homogeneous conditions were found to have the smallest impact on the pack charging efficiency reductions. After establishing these trends, various cost metrics were selected to perform a techno-economic analysis of plug-in hybrid electric vehicle ownership in Great Britain. More specifically, these parameters included both the costs incurred by the vehicle owner as well as the external costs of PHEV ownership. Included in the personal cost calculations were the levelized fuel cost savings, which exemplified the financial benefits of owning a PHEV compared to an internal combustion engine vehicle. Thus, I found that the more the PHEV is used in Great Britain, the greater the benefit to the vehicle owner, reaching a maximum of £6,800 in 2035 for a petrol PHEV. Crucially, the reductions to these benefits due to pack degradation will be highly incremental, as the largest calculated reduction was 0.05% in 2035 relative to the reference case that excluded any degradation. Nevertheless, to expand this analysis, another cost metric was studied, namely the levelized cost of charging. The LCOC accounts for the capital and operational expenses of purchasing and using an EV charger, and assumes that these costs will be allocated to the electricity this device supplies to the vehicle battery. By introducing the considered degradation scenarios to the LCOC calculations and obtaining the LCOC value for 14 distribution network operator areas in Great Britain, I found that even the largest obtained efficiency reductions will introduce highly incremental changes to the baseline LCOC values, which incidentally were calculated by excluding any degradation effects. Crucially, since the costs in the LCOC formula are offset by the supplied energy, the reductions in the battery charging efficiency can drive the total LCOC down by a maximum of 0.058% in 2035 relative to the baseline. This results in marginal improvements in the financial viability of owning a PHEV in Great Britain. Nevertheless, since PHEV energy demand will increase with degradation, a negative effect on the society can be expected. By studying the grid mixes in the 14 DNO areas of Great Britain, as well as the future forecast for grid decarbonisation, I found that the established pack efficiency reductions can increase charging CO2 equivalent emissions of a PHEV. Though the calculated increases were found to range from 0.37 to 1.25% relative to the reference, even such small changes can still be significant if left unaccounted when a fleet of vehicles is considered. This finding consequently serves as an indication that much more effort must be made to decarbonise the British grid, with additional emphasis being on the areas of the East Midlands and South Wales. In conclusion, this project indicated that in a developed country such as the UK, where a considerable share of renewable energy generation is present and where energy prices are due to fall because of the accelerated introduction of sustainable energy generation technologies, the transition to PHEVs will aid in achieving a key part of Goal 11. Still, this conclusion is not all-encompassing, as many considerations must be made when calculating the value of, for example, the LCOC. The effects of parameters like future electricity costs are significant, and thus if even the smallest differences are present compared to the values used in this study, those should be accounted for and duly noted in any subsequent calculations and research projects. Thank you very much.
Thank you, Daniel. I am Imran Mohammed Marwa, and my thesis investigates the utilization of natural gas as a resource to ensure energy security and enable a just transition in Nigeria's power sector. Accordingly, my sustainable development goal focus will be on number 7, affordable and clean energy access. Firstly, good evening, everyone. We've been plagued by the dirty footprints of the broken grid in a lot of developing nations. These countries do not produce nearly enough electricity to satisfy demand. So many people use diesel and petrol power generators like this one at home or at their place of business to produce their own electricity, which is very bad for the environment and the economy. Self-generation meets almost 50% of electricity demand in Nigeria. And the emissions, according to the size of generators seen in the clouds, is significantly high, relatively as harmful as coal plants in small and medium applications. For the economy, studies by the National Bureau of Statistics estimate generators and fuel costs to contribute in making locally produced Nigerian goods over 30% more expensive than their imported counterparts. But Nigeria has great proven natural resources, such as about 15 gigawatts of small and large hydro, the 9th largest natural gas reserves in the world, and enough solar to power the whole of Nigeria using just 0.1% of the landmass for solar farms. Initially, I wanted to investigate out of Nigeria's many abundant resources, oil and gas, coal, solar, wind, how an energy mix can be formed to champion its transition into providing energy security in the power sector, and thus reducing the use of these petrol and diesel generators, and hence reduce emissions. So I undertook this analysis by using the World Bank's multi-tier framework, as seen on the left, under the Sustainable Energy for All initiative. These tiers focused on not only energy accessibility, but also on quality and affordability of electricity, which recapitulates on the focus and its importance, which is SDG number 7, affordable and clean energy. I then specified the demand requirements across the rest of the sectors. So I looked into the industrial, commercial, and exported electricity demand, which is driven by factors such as increase in population and economic growth, industrialization, and I also had to itemize the supply sector, which is the power plants, available capacity, efficiency, and etc. So subsequently, I formed 3 scenarios for the investigation as follows. A business as usual scenario that would continue as per usual with slow policy implementation as per historical data shows and an increasing auto generation capacity. A renewables focused scenario that would follow the national renewable and energy efficiency policy long-term targets closely, and then a natural gas centered scenario that would cut gas constraints such as pipeline losses, gas flaring, and improve on building infrastructure and capacity. For the results, we see that the business as usual scenario falls considerably short of meeting demand. However, both other scenarios have achieved energy security in the sector, as there are no unmet requirements. As for the greenhouse gas emissions, the gas scenario reduces emissions in comparison to the baseline by 643 million metric tons, and the renewable scenario does this by about 1.5 billion metric tons of carbon dioxide equivalent. Lastly, the investment costs of the gas scenario amount to $42 billion over the years in comparison to the business as usual, and the renewables counts to over 125 billion American dollars above the business as usual, which makes the renewable scenario difficult to overcome, especially considering a developing sector that is underfunded, as is Nigeria's power sector. So in conclusion, with that being said, after iterating the model a few times and applying different policies as well, a mixed energy system would be optimal, where gas, being the most financially sustainable option, can be used to achieve energy security, and renewables can also be utilized to further reduce emissions. Because solar and hydro potentials are largely undertapped still and could prove very necessary to achieve energy security and a just transition. And instead of going all out on renewables in this way, the power sector can be much easier financed and developed. A just transition will then be justified in the resultant jobs that are created and the ease of doing business that is enabled. Thank you for your time. And now Sebastian will take us to South Africa with the same SDG focus.
Thank you, Imran, for talking us through how gas may contribute to energy security in Nigeria. My name is Sebastian Kern. The topic of my thesis is the economic potential of offshore wind in South Africa. This addresses the SDG number 7, affordable and clean energy. To start, it is important to clearly state that South Africa is facing an ongoing energy crisis. The lack of investment in new generation capacity and the lack of maintenance of its existing coal power plant fleet has resulted in continuous scheduled load shedding. South Africa needs to urgently solve this energy crisis, and despite other renewables starting to develop, offshore wind has not been on the political agenda at all. However, South Africa boasts considerable offshore wind resources. Its exclusive economic zone, this is the area in the ocean in which South Africa rules, has high average wind speeds of up to 11 meters per second. While gross and technical resource potential have been evaluated at 3,200 and circa 500 gigawatts respectively, economic resource potential has not been. To address this, my research employed a net value approach. Levelized avoided cost of electricity, or LACE, represents the revenue available in the market for installing an offshore wind farm. Therefore, think of LACE as equal to revenue. Levelized cost of electricity, or LCOE, represent the cost of installing an offshore wind farm on a per unit of energy basis. Therefore, think of LCOE as equal to cost. By subtracting LCOE from LACE, or cost from the available revenues, a net value can be calculated. This was done for over 6,000 locations in the South African exclusive economic zone. Given the data and assumptions used in this study, South Africa has an economic potential for offshore wind of between 5 gigawatts and 8 gigawatts, depending on market conditions. In the normal scenario, 5 gigawatt of offshore wind capacity are economically feasible without subsidies, and an additional 3 gigawatt of capacity become economically feasible with subsidies of 47.6 billion rand over the lifetime of the assets. This result is robust across most scenarios, although required subsidy amounts vary. Results are significantly impacted by changes in capacity factors, but also electricity prices, water depth, and weighted average cost of capital, or WACC. An important result is that technology costs become prohibitive for higher water depths. Currently, floating foundations are just too expensive, but prices are likely to decrease in the future. WACC, however, has the single largest impact. With a considerably deflated WACC at 5%, an additional 129 gigawatts could be made economically feasible with reasonable subsidies. Therefore, the provision of low-cost capital is a key factor for successful project development. The results of the study were contextualized using innovation theory. Policy support needs to be available as soon as possible. The questions are what to do and how to do it. Regarding the what, South African policymakers need to do 3 things. First, they need to broaden South Africa's existing auction processes to include offshore wind and set up a tendering scheme for offshore licenses. Second, they need to establish a system builder, an independent organization that could manage the offshore niche and provide a mediator between public and private stakeholders. This has been very successful in the UK. Third, they need to work towards improving South Africa's project financing conditions in the form of the cost of capital for equity and debt. This would not just help offshore wind, but the development of new generation capacity in general. Regarding the how, policymakers need to move from clear goals to coalitions, mobilize through policy, and continuously evaluate this policy. In conclusion then, South Africa is at a crossroads. All things considered, offshore wind may just be the right bet. Thank you.
Thank you, Sebastian, for presenting us your project in South Africa. My name is Fatima Mosin, and now I will move towards the north of the African continent and focus on SDG number 6, clean water and sanitation. My project consists of a life cycle analysis of storage batteries for photovoltaic water pumping systems in sub-Saharan remote areas. Water scarcity in Africa is still an important concern, and the COVID-19 crisis has highlighted its importance for water sanitation. Still, 2.2 billion people are lacking safe drinking water. As it can be appreciated from the picture, most of the people who suffer from water scarcity are located in the African continent. PV water pumping systems have proven to be an interesting solution from both a technical and financial point of view to provide water access in these remote areas. PV water pumping systems are usually made up of 5 key elements: a PV array, a controller, a motor pump, a fountain, and some pipes. These PV water pumping systems are usually accompanied by a storage technology in order to provide water access when the sun is not shining. Depending on the storage technology, 2 architectures can be defined: water tank storage, where the energy is stored in the form of water, and battery bank storage, where the energy is stored in the form of electrochemical energy. This PV water pumping system was installed in Gogma in 2017 and has been used as a case study for this thesis. Gogma is a village of 215 inhabitants located in the center-east of Burkina Faso. In previous techno-economic studies, it was found that the life cycle cost of the water tank architecture was around $31,000, whereas the life cycle cost of the battery architecture was around $24,000. This finding brings new opportunities and the possibility to decrease the cost of water in these remote communities. But these batteries are usually characterized for the environmental impact, especially due to toxicity and scarcity of some metals. Therefore, the aim of this thesis has been to quantify the environmental impact of these storage technologies and develop a methodology that would allow the integration of these environmental indicators in future studies. Life cycle analysis has been the selected approach for this study, which is the most comprehensive method when quantifying the environmental impact of a product or a service. All the compiled information was organized, and there was a total of 24 scenarios. These scenarios were classified per storage technology, per location, and per end-of-life treatment. There were 3 areas of focus: China, Europe, and Africa. And all these scenarios go from material extraction to disposal, what is known as cradle to grave. There were 2 scenarios for the steel water tank, 4 scenarios for the plastic water tank, and 9 scenarios per battery technology, lead acid and lithium-ion batteries. The presented results are the ones from the 6 best scenarios, which were selected from the previous analysis in the 3 endpoint categories: human health, ecosystem, and resources. The 5 midpoint categories that have been analyzed are the ones represented in the y-axis. Results are presented in percentages, and as it can be appreciated, lithium-ion batteries and the plastic water tank are the solutions with the lowest environmental impact, while lead-acid batteries and the steel water tank are the solutions with the highest environmental impact. To conclude, 2 functional units or units of comparison have been analyzed. Therefore, 2 conclusions can be made. The first one was meeting Godsma water demand, where lithium-ion batteries and the plastic water tank were the best environmental solutions. The other one was per kilogram of storage technology, where both water tanks, plastic and steel, represented the best environmental solutions. The viability of both architectures has also been analyzed, and the main issues were that water tanks could provoke sediment obstacles and therefore poor water flow, and that batteries will need various replacements during the 20-year lifetime of the pivot and puppy system. One for lithium-ion batteries and up to 4 replacements for lead-acid batteries. Regarding future developments, 4 areas have been identified. Estimating lithium-ion battery bank size and lifespan, considering that this was based on assumptions. Including plastic water tanks and lithium-ion batteries in future techno-economic studies. Keeping life cycle inventories updated, especially for lithium-ion batteries. And finally, developing new environmental coefficients, considering that only the global warming potential has been developed. Now, my colleague Daniel will finish with the conclusion. Thank you.
Having presented our findings from our respective research projects, we can now move on to our conclusions regarding the global ability to achieve sustainable development goals. It should first be noted that the projects conducted by the members of our team clearly highlight that computational approaches are of substantial benefit if the ability to achieve sustainable development goals needs to be evaluated in any part of the world. Nevertheless, to perform such analyses, a careful consideration of a wide spectrum of variables is vital, and since the required parameters will change depending on the socio-economic specifics of the selected geography, making a universal conclusion regarding the steps necessary to achieve either of the discussed sustainable development goals will be erroneous. Though we showed that transitioning to plug-in hybrid electric vehicles can ensure sustainable and affordable transport in Great Britain, the same might not be said about countries like Burkina Faso or Nigeria, where electricity costs could be prohibitive and the local grid mixes could lead to substantially larger external costs of degradation. This statement can be backed up by simple comparison of the average grid mixes of these two regions, which illustrates only one of the considerable differences that currently exist between developed and developing parts of the world. What is more, though the introduction of wind energy in South Africa is achievable by following the policy suggestions made by Sebastian, it is possible that in other African countries characterized by greater levels of social and political unrest, such steps might simply be impossible to make. Consequently, if these considerations are neglected, key objectives of Sustainable Development Goals will be omitted, which could lead to ineffective conclusions and recommendations. As such, any further projects and research must be conducted with caution and due diligence. Thank you very much indeed for your.
Thank you, Group 3, for your presentations. I would now like to introduce Marine Lanet, who is a senior consultant in sustainable development at Nomadeis, and she will lead the remainder of the discussion for this session.
Good afternoon, everyone. First of all, congratulations. I graduated from the SCF Master a few years ago, so I know the commitment this master thesis represents. I did my own thesis on energy access in remote areas, so it's a pleasure to participate again to the SCF annual conference and to have the opportunity to ask you questions about your very interesting work. So yes, currently I'm a consultant in sustainable development, but I will very soon go back in academia and start a PhD on the impact of climate change at the local level. We only have 30 minutes for this discussion, and I would like to hear each one of you. So let's start. Maybe we can follow the presentation order. So first, Livio, if you were a policymaker, now what will you do? You've learned a lot during this thesis. You have interesting results. What are the next steps?
Yes, thank you. That is a great question. So focusing on the urban transport and land use sectors, which is where my dissertation really dove into deeply, I think 3 major policy recommendations come out of it. They are somewhat generalized, and they can be applied throughout Europe and North America and most developed countries. So first of all, one thing that was really highlighted from my findings, both from the systematic review I conducted and from the modeling case study in London, was that the health co-benefits and economic co-benefits and social co-benefits of active transport are huge, and they really need to be harnessed if we want to accelerate the transition to more sustainable cities. So what I mean by that is when right now there's a large focus on electric vehicles or hydrogen vehicles, and yes, those are great solutions and they definitely have to be integrated into our future. We should really be focusing as well on redesigning cities for active transport, so providing bike lanes and different pedestrian infrastructure, as this generates co-benefits. For example, the physical inactivity benefits really are substantial, and you can save hundreds of lives every year. In London, for a 20% reduction in traffic, it came to over 300 lives. And of course, this comes with huge economic benefits as well. Or looking at the social aspect, if there is tactical, another important policy move must be to try and leverage the interconnected nature of these sectors and use a systems thinking approach. So as you integrate more active transport and cars are removed from the street, there should be some tactical urban urban green space development in cities, as this can bring not only economic, not only environmental and health benefits, but also really increase social benefits and mental health and some unquantifiable aspects of the transition. So in conclusion, if you find a way to leverage the systemic nature of the cities, cities are really placed in a great position to somewhat leverage the climate change battle and themselves be leaders in the transition to more sustainable and healthier and resilient cities.
Yes, thank you very much for the insights. So maybe let's move to Ajai. Can you explain why you choose these 3 particular performance indicators, water saving, efficiency, payback period, and carbon saving? Did you think about other indicators you maybe then excluded to simplify the model, but indicators you could add to maybe go a step further in for future work?
Yeah. Okay, that's a very great question, because actually when I was doing the model, I considered more than just 3 indicators, and I present you with the 3 main key indicators that I would like to use as a standard to pick up my optimal design. I also consider about the rainwater use efficiency and the total empty days for the tank for the storage tank, and I have also considering the annual money saving that could be used in the payback period calculation. And actually, for in the future, I think my consideration for the economic indicator is not enough. So in the future, if more economic indicators such as the net present value can be taken into consideration, the model will show a better perspective in economic. And for the environmental impacts, I have only considering the carbon saving during the operation phase in the simulation model. And I also have an LCA model that used to investigate the whole life cycle environmental impacts. So in the future, if those 2 models can be combined together, I think the environmental impacts will be evaluated from a whole life cycle perspective. Yeah, thank you.
Great, thank you. So Blanca, how do you think your methodology is replicable? I mean, for example, if you want to carry out a similar study in another country, let's say China or Kenya, do you know which part of your modeling should be adapted? What are the things you should consider and look more precisely?
I think one of the things that you should look more precisely is the collection system. Basically, because in many of the undeveloped countries, they lack of that collection
stage, and as well they don't have a treatment capacity, so it's way different. For example, one of my main conclusions was that electric trucks are going to become one of the future's alternative for the collection stage, but if there's no electrical grid infrastructure that is reliable for charging the vehicles, it's impossible to extrapolate the solution.
Okay, thank you. Thank you very much. Arthur, we have 2 questions from the audience. The first one is, to enable deaggregation, what kind of ICT infrastructure may be needed, and is existing system sufficient?
Yes, so thank you for that question. So the idea behind the research is that it would actually be more of financial agreements that are between the different actors themselves. So I could see it like from just the way our grid is right now, you definitely could implement it right now because it's more about having those kind of agreements and just having that governance between businesses to actually be like, okay, I'm going to be producing like more energy at this point, which I mean, we can know how to quantify the amount of electricity we're going to be producing at least. So you could definitely be doing it because the idea with it is that you're not actually transporting, in terms of virtual PPA, you're not actually transporting the electricity from one building to another, you're just sending it to the grid, and then just through monetary value, you're doing this transfer of like renewable energy credits towards one building from one building to another. So I definitely think we could do it with the current like grid and the way it's now. What I would see in terms of what needs to be implemented though is that government structure. So a governance structure, you can't like to actually have those agreement work and have it implemented at such a scale of aggregation between smaller businesses. You're going to need a lot of cooperation, and you're going to need to have like a body on top of it, just actually making sure that everything is, well, every actor is obeying what they need or everything is working well.
Okay, thanks. And we have a second question from the audience, which is, this 20% of increase, was it evaluated economically? What this would mean in NPV, LCOE, IRR improvement?
Yes, so this was decided not to go too much into that focus with the research, as the NPV, LCOE and all are a little bit dependent in terms of what type of businesses you can actually do and how the solar is actually like placed on the different buildings. So it was decided to just look a little bit more in terms of what would be the role of different buildings in case you created this aggregation structure. But what I would think of in terms of what was done in previous other places or just what was already being done with OPDC, I do think it would definitely decrease the like overall NPVs of the different solar project. So it would it would increase, the NPV. So the overall value of the project would be higher, as they would see that with aggregation on a specific building, for example, if you do increase pretty much the size of your project, you can benefit from just purchasing solar panels or just installation at a lower cost. And so you can actually decrease that overall initial capex and make it more profitable. But having exact value was a little bit outside the scope of the project itself.
Okay, and do you have any idea of what would potentially be the advantages and drawbacks of adding storage to the system?
Yes, so I mean, definitely, like I do see how adding batteries or just overall storage could definitely improve, I guess, their overall amount of solar that can be placed. Because if you're pretty much producing more than what the buildings need at noon, which is even if that's at the peak of when businesses usually are like using electricity, storing that and using it later could definitely be beneficial. The project itself was trying to look a little bit more in terms of in an urban area, would you really need that storage? Or could you actually try to implement more solar without actually implementing solar? Because as we know, batteries currently, in terms of, as Fatima showed a little bit, in terms of just LCA is not like the best. I do think, though, there is value, and a future project could be looking at that in terms of just the electric vehicle implementation that could be done in like such a industrial park. So there's going to be a lot more implementation in terms of EV trucks and all. So I do see how there could be value just in using those and trying to understand how the fleet could be managed to actually benefit on top of that the solar.
Okay, thank you very much. Daniel, so you choose MATLAB to carry out your analysis. You showed us a great graph of your model. Can you explain why you choose the MATLAB and Simulink programming language, and maybe what are the difficulties you faced to try to reflect the reality into a model, because a model is physical equations. So what are the difficulty you faced?
Sure. So for starters, regarding the choice of MATLAB, that was primarily driven by the reduced computational complexity, because realistically, upon trying to select the model, there were two real options. One was trying to go the more physically accurate, but ultimately more complex route, using something like Python, for example, with my project supervisor having developed a very useful Python tool called PyBAM, which is based on partial differential equations and thus is capable of modeling the diffusion of particles much more accurately within a battery pack or within a cell, but ultimately it leads to greater levels of complexity. And as such, because the time scope for the project is very limited, or rather was very limited, it would have been very difficult for me to reflect all the scope. So I considered 5 different thermal conditions in my project. So carrying out those simulations would have required a considerable amount of time. Whereas in MATLAB, because the physical accuracy is sort of simplified, though not neglected, it's just simplified to a more simple equivalent circuit model, which is just literally a combination of resistors and capacitors, which are used to reflect how a battery would behave. The simulation times are much shorter and can be run pretty much on any machine, and as such, I could really, do everything that I wanted to do with it. However, still, the physical accuracy will be marginally reduced. And for my project specifically, I did have to reduce it a little bit more. So specifically, my original model was provided by Dr. Yan Zhao, and that model was comprised of 3 resistor-capacitor pairs, which in essence makes it more accurate in terms of reflecting the internal resistances of the cells, as they're comprised of multiple terms, both ohmic and polarization. So still, though adding accuracy, it increases time. As such, I had to reduce it, downsize it to a 1 resistor capacitor pair, and that kind of made all the resistances to be lumped together. Though it did not make a major difference just because of the simulation conditions applied, it still simplified the model and resulted in relatively accurate fits to experimental data, which I based my entire project on, namely the data provided by Dr. Max Nader-Marlow. Though a difficulty, it still nevertheless ensured that simulation times were shorter and the accuracy was not majorly impacted at all.
Okay, thank you. And if you had more time to carry on this work, to continue your research, what would be the first thing you would like to do to go a bit further?
I would personally try to tackle and expand the model because realistically what I based my subsequent techno-economic analysis on is a relatively simple use profile, which implies going from 100% state of charge to 0 and back to 100, which was one of the primary reasons why a plug-in hybrid electric vehicle was chosen, because such a cycling profile is perhaps more representative of such a vehicle. But still, in reality, a person would never use their vehicle in such a way that they completely drain the battery, the storage of energy, and then completely fill it back up. So if I were to alter the model to reflect this greater variability in user behavior and in the way that a battery is used, I guess it would have implemented a greater level of accuracy into a real world sense of how the battery would be used to what it would be subjected to, and ultimately lead to a greater level of accuracy in the conclusion regarding the cost impact.
Okay, thanks. Thank you very much.
Thank you.
Imran, could you explain why the greenhouse gas emissions of the renewable scenario are higher than the gas scenario?
Hi, Maureen. Can you hear me?
Yes.
Okay. Thank you for this, and congratulations on your PhD offer as well. So it's simply because the renewable energy targets that Nigeria had for 2050 had about 90% of renewable energy generation. So we maximized the hydro potential as well as the PV generation, including solar home systems and utility scale as well. So the difference is that natural gas that was mainly used for the gas scenario still emits about 500 grams of carbon dioxide per kilowatt hour, whereas the renewable scenario that was 90% renewable technology had 0 grams zero emissions. I hope that answers your question.
Yeah. So in the renewable scenario, there is solar, hydro, and is there, for example, other sources such as wind?
Yes, there's a bit of wind, but it wasn't as substantial as the first two I mentioned. I think wind and biomass primarily took only about 5 to 10% of the overall energy mix.
Okay. And so when you talk about the greenhouse gas emission, does it also take into account the embedded emission, the greenhouse gas that are emitted when you create the system, when you manufacture the system, or only the emissions during operation?
In the thesis, we included the embedded emissions, but for the results in the table that we had, it was only the direct emissions.
Okay, and so how does it affect the results if we take the embedded emissions?
Yeah, the embedded emissions are still, as you can imagine, much more significantly reduced in the renewable scenario. Similarly.
Okay. And so maybe one last question. So you talked about the investment costs. Does it only include CapEx or also the OpEx?
It includes the OpEx as well. So we split the OpEx into fixed costs and variable costs. And as you can imagine, the variable cost was only applicable to the natural gas scenario, mostly that has gas as a fuel, whereas the others only had fixed costs in the renewable technologies. However, the CapEx was still substantially much larger, so it contributed to most of the costs. Okay.
And if we look at the three scenarios, what are the main reasons, like the most important elements that makes the investment cost difference between the three scenarios?
Yeah, so the first one was the business as usual, which just counts the increase in self-generation, which is petrol and diesel generators. But the difference between the last two, the natural gas and the renewables, is actually buying the software, the hardware, the PV systems, for example, building hydropower, as well as the storage systems to go in place to maintain the grid stability.
Okay.
That's what made it substantially more expensive.
Okay, thank you very much for your answer. Sebastian, we have questions from the audience. First one is, what is the current development status of onshore wind in South Africa, and how should the onshore and offshore development be coordinated?
Yeah, hi there, Marine. Thank you very much. Thanks also for the question. Yeah, it's a really good question. So onshore wind in South Africa currently stands at about 2.5 gigawatts. There have been ongoing tender rounds, both for solar and for onshore wind, together with other generators. A new round has not been announced so far, but it's very likely that more wind projects will come up onshore. And in terms of coordination with offshore development, I think it's somewhat tricky, other than also including offshore wind in the very same tendering scheme that is currently in place, which is actually very, very good, simply because the technology is quite different, and South Africa's bathymetry is fairly extreme, with an extreme drop off just a few hundred meters off the coast. So most likely, most of South Africa's potential lies in floating offshore wind. And so therefore, yeah, the technologies are quite different.
Okay, And another question, well, more a remark from the audience is grids and ports availability, which would need to be also improved. Like, what are your thought about this reflection?
Yeah, another really good question. So grids is a little bit easier to answer. Both Cape Town and Durban currently have a 765 kilovolts export line installed, and most of the currently economically feasible locations are within that area. So it is likely that offshore installations in those areas could tap into those export lines to bring the electricity to the rest of the country. So that would actually work fairly well. In terms of ports, that might be a little bit more tricky. Nowhere in Africa, on the African continent, do we have offshore wind so far. So most likely, most of the vessels would have to come from other areas in the world. I know that currently in the US, the installation of the first major offshore wind farm is undertaken with ships from Denmark. So it's not completely infeasible to bring these ships down to South Africa. But certainly that would add to the cost. And so if actual project development was to take place, then that would need to be something to be taken into account.
Okay, and so offshore wind seems to be interesting for South Africa from an economic perspective, point of view. So do you know if there are some specific national and socio-political obstacles to be overcome in the country before developing offshore wind there?
Yes, I think so. So firstly, I think South Africa is trying to position itself as somewhat of a testing bed for floating offshore wind. There's one development cooperation currently ongoing with a Swedish developer and some local interest groups. So that might be something that would be very helpful, and certainly, fostering these types of investor communities would be something that South Africa would hugely benefit from. In terms of the obstacles, I think simply for bringing these larger wind parks online and for distributing the subsidies between them. Currently, the energy provider Eskom is still very much in the system for this. And since Eskom owns most of the generators that are still running with coal, they have somewhat of a vested interest in keeping them running. And so in the past, this has resulted in them delaying the agreement to some of the power purchase agreements that independent power producers rely on to get their projects off the ground. And so if this was to continue, with larger projects such as offshore wind projects, then that would certainly be a pretty big problem. So South Africa is partly addressing this already by trying to split Eskom up into different companies that are concerned with transmission, generation, and distribution. So that might help in the future, but certainly trying to investigate some of these incentives for Eskom as the energy supplier, and then potentially also further investing in independent power producers that are interested in developing offshore there, I think would be the way to go.
Okay, thank you very much for the answer. And so, Fatima, last but not least, your work focused on the environmental impacts of the storage system of the PV water pumping system. You also mentioned in your introduction the costs of the system. Could you think about other elements or system characteristics that have to be considered when selecting the storage solution for a specific location? I mean, for example, maybe the availability of people that could be able to repair the system. Like, do you think about other elements?
Yes, so thank you for your question. And actually, there is also a question in the panel that has also a bit to do with that. So here, of course, I only mentioned the cost because the cost is one of the key elements, especially for these communities that cannot afford a high cost. But in the discussion, even though the results that have been presented were the quantitative results, another really large discussion has been done qualitatively regarding the availability of these resources, because it's not the same getting a water tank than getting a battery, as well as recyclability, if there are any recycling facilities, same as maintenance, because as I mentioned at the end, the viability of the systems, water tanks, they wouldn't need any replacements during the 20-year lifetime of the water puppy system. However, lead-acid batteries, they will need up to 4 replacements, and lithium-ion only 1. But yet, because also in these communities, there is a big lack of access to this technical knowledge. So one of the things that was mentioned is to maybe have a team that is trained before these systems are installed, and then maybe they can carry out all the O&M activities for these systems. And also answering the question about if the depletion of underground water sources has been analyzed, not from a quantitative point of view, but it's also included in the discussion that in previous analysis, it was found that battery storage, they lead to less variation in the water borehole, what contributes to the sustainability of these underground water sources when compared to the water tank. It's also good mentioning that before these PV water puppy systems are installed, the underground water sources should be analyzed in order to position the PV water puppy system in the resources that have the largest amount of water. Okay. I think I've answered your question.
Yes, thank you very much. There is a last question in the chat, but time is up. So it's a general one addressed to the whole panel. So maybe if you want to write your answer instead of answering during the presentation, I maybe leave the floor to the organizer of the presentation.
Arthur, do you want to jump in?
Yeah, I'll just answer in the chat.
Okay.
Well, in which case, thank you, Maureen, for leading such an interesting discussion, and thank you to all the panel chairs, our keynote speaker Stephen, and to all the students who have presented today. I will now pass over to Faye, who will conclude the conference.
Thanks, Anna. Right. Excellent presentations and discussions. I think this really demonstrates your knowledge and your experience together with us at as the SEF students. It is now coming to an end, isn't it? It's not only for the end of the session, and also probably it's end of your time with us as a SEF 2.0 students. However, if you think it back, the time really flies. I still remember when I sat with some of you in the bunker and try to introduce myself and say how new I'm as new as you are. When we started, as this is also the first year to work as the course director. Now you are finishing your degree, and in a few weeks' time, when the new cohort comes, I can say that you guys listen to me. I have more experience than you, right? So really, it's my privilege to work with you, to learn together, to improve over the past year. I think you all done incredibly good job. SEF is one of the most popular and challenging MSc course in energy in my mind. So that particular in this current pandemic situations, that some of the session have to be delivered remotely, and you guys cannot really work most of the kind of time together in person, but you all done incredibly good job. I'm so proud of you on the achievement. I believe also your friend and family will join me to congrats for your achievement over the year. I would also want to say that today and also yesterday's session in particular has demonstrated your success, but not only as an individual, but also as a group, as a cohort, which is really what we want to achieve as a SEF course. You guys came from 25 different countries to form our 21-22 SEF cohort. Now I can proudly to say that you all ready to start your next journey and play your role in the energy transition. Very soon, you will become one of our over 500 alumni of our SEF network. I do hope we all keep in touch, and together we make the difference to the world, to the energy sector and beyond. So to conclude, I would like to thank again our excellent keynote speaker, Steve, and also our panel hosts, Piotr, Maria, and Ajai. Of course, our student organizers who commit quite a significant amount of their own time to make this conference possible, Avik and Nadia, and also our staff member, Connor and Gavin, who have really made this conference possible. I would also to thank all the audience and all the questions that really make the event memorable and beautiful. For the audience who are interested in our student work, please do get in contact. We also regularly have collaborative research project for the students. And for the students that join us will for the next cohort that in the conference, I look forward to see you in a few weeks time. I think with that all said, I would like to conclude the conference and wish all the best for our students. And for some of you that currently in London will join later, we will see you. For others that you cannot join today, I do look forward to see you perhaps in the graduation ceremony in a few months' time. Thanks you all. See you soon.